Welcome to the 2021 Texas A&M Physics and Engineering Festival. The festival started in 2003. Ed Fry, Texas A&M distinguished professor and a great visionary, founded the festival. He asked other professors to build a hands-on demonstration that inspired them when they were students. The very first festival had just a dozen of hands-on demonstrations and a lecture by Stephen Hawking. Since then, it has become an annual event. The best speakers in the country, famous physicists, astronauts, present at our festival. The heart of the festival is 200 of our hands-on demonstrations. I love our festival. I love this atmosphere when thousands of people get together to celebrate science.
During the amount of time that I was there, I got to see this physics festival grow from a relatively modest-sized event all the way up to the huge yearly event that it is now, where they routinely are able to bring thousands of people to the Texas A&M campus.
And they're coming to be excited to celebrate, physics, engineering, and science.
It's really one of the most unique events that is on Texas A&M's campus. The event itself brings together people of all ages from around the world to experience the joys and wonders of science.
You see people that are from 5, 4, 3 years old to 60, 70 years old, and everything in between coming together to learn science.
Another cool thing about Physics Festival is to watch this person with a long and amazing scientific career, how this person is happy to explain simple and beautiful physics to other people, to kids and adults, instead of sitting in their office and writing some scientific manuscripts.
Talking to dozens and hundreds of people throughout the day who are all excited to see something about physics. And it's such a different energy than teaching or doing your research, and it's all packed into this one day. And it really just honestly makes it the best day of the year.
One of the most rewarding experiences for me was watching as the kids would have the little aha moments as they see these little demos of things that they experience in their day life, and they have it explained to them. But then you look behind them and you see their parents and their grandparents having the same experience where they're learning things that they didn't know as well. So it really is an event that reaches all ages and touches home to anybody and everybody.
But when you really do make that deep connection and you see a young person get excited about what you have to tell them and the science behind it, that connection's immediately obvious, and you've made an impact on them, whether they choose to follow that career path or not.
The demos that the Physics Festival has cover everything between space science and optics and engineering, and the participants get to play with lasers and they get to play with semiconductors, and they just get to really see how everything works and really be an active participant there.
I found students coming back and people coming back and learning and knowing more about the demos than they had before when they first came.
For example, when you explain some physics demonstration to a kid or adult, and they got so much excited about it and about the physics behind it, so that they come back to you with a friend in an hour, and they're like, oh, you don't have to do anything. I know how the demo works. And they start to explain it to their friend. And that's how the excitement about physics gets transferred in chain reactions.
The Physics Festival is really like a blessing for the community in that it allows young folks to get exposed to every area of physics and engineering in such a short amount of time that the likelihood that they're going to find that sub-area that they're really passionate about and they might take as a passion or even a career choice through their life is much higher.
The first time that I just attended, I was so overwhelmed. There were so many demos on so many different topics that it was just hard to imagine what I was going to see at the next booth. It was really awesome to see professors and students working together, and these weren't students that knew it all. These were students from all levels, just explaining what they knew, and having a good time with it.
During my graduate student orientation, when I was visiting the department, I happened to come during the weekend when the festival was taking place. And what was so exciting for me was seeing this event in person and getting to see how excited the entire department was in being involved. Everyone from faculty to staff to students, graduate students and undergraduates alike, just so passionate about talking about discussing science and seeing people coming from everywhere who were just as excited to see all of these demos and see these talks and get to experience science in this really just amazing way that we don't always get to do in classes. I had such a great experience with the festival that weekend that I decided, hey, I'm coming to Texas A&M. And so I signed my acceptance letter that weekend, turned it in, and I have never looked back.
The first time I went to the physics festival at Texas A&M was in 2011, where I was visiting with the grad school. And that actually helped significantly in making my choice for which grad school I wanted to go to. The next year, I was adamant about being involved in the physics festival. And that is one unique thing about this physics festival that is completely different than any science festival that I've seen, is that this engagement with the community is long-term. It's not just a one-time festival. And the diversity that is included in this festival of faculty members and students and graduate students all helping with giant smiles on their face and learning science together with the community is something quite exceptional.
You know, I look back on my experiences with the festival with fondness. In particular, those long nights the week before the festival, building demos with our team, trying to get things to work at the last minute. And you know, those nights, they were tiring, they were exhausting, but it was all worth it in the end to see people's faces at the festival. Not only that, but they gave me the confidence I needed to pursue bigger projects like this, an airplane build with my husband.
As a participant, it's a lot of work to pull together. We have days and weeks of preparing and getting demos out and just making sure that everything goes well. But it is so much fun. I get to work with different people that I usually don't have the chance to get to meet, and while we're putting the festival on, we get to talk to people from all different backgrounds, from all different ages, from all different experiences, who absorb this information and make different analogies, which leads to so many interesting conversations.
In fact, I was so inspired by my time in both the outreach program at A&M and also my work with the physics festival that I've actually since started my own outreach program here at Rice University, and many of the aspects of it I've modeled off of the things that I learned and the things that I saw during my time at Texas A&M in the Department of Physics.
It's an experience I would do all over again, and I wouldn't trade for anything.
I really hope that you get a chance to experience in the same way that I did, even in this virtual environment. And I hope that we get to see you in the future here in person.
And so, even though the festival is virtual this year, I hope that you can get a taste for that at this year's festival. You know, experiencing physics and all the beauty that it has to offer. So, get go Aggies, and I hope you enjoy this year's festival.
Welcome to the 2021 Physics and Engineering Festival hosted by Texas A&M University Physics and Astronomy. I'm your host, Morgan Nasser. We were all saddened to have canceled last year's festival due to COVID-19, but now we're back live all over the world. We have a great lineup for you today, and we hope all of you enjoy, no matter your age. Physics helps us understand the universe, but it's also extremely cool. We would like to first thank Halliburton, Colonel Halshade, Class of 67, and our Spirit of Giving crowdfunding donors for making this year's Physics Festival possible. Remember, if you have any physics questions, ask them. We have a panel of experts in chat ready to answer them. And if you ask an especially awesome question, we may answer it here in the studio. Want your name featured on the screen? Simply click that red subscribe button, and that's all there is to it. Also, be sure not to miss a chance to win a surprise bundle of science goodies like a t-shirt, glow-in-the-dark frisbee, skyhook, diffraction glasses, and more. Simply go to tx.ag/science giveaway. There's also a link for that in the description as well. Starting in just a couple minutes, we will showcase our first round of physics demonstrations like dancing fire, potato physics, and methane bubbles. Soon after that, we'll have our first key speaker, Dr. Nancy Currie-Gregg, who is a NASA astronaut and professor here at Texas A&M University. Following her talk, be sure not to miss our second round of physics demonstrations like infrared imaging and super cool superconductors. Then we have our second key speaker, Dr. David Saltzberg, who is a science consultant on the CBS hit comedy TV shows The Big Bang Theory and Young Sheldon, as well as a professor at UCLA. Following his talk, we'll jump right into our last round of physics demonstrations like magic bubbles, Tesla coil, and 5-barrel explosion finale that will surely blow you away. Last, we'll give everyone the opportunity to interact with scientists and more demos in our Zoom rooms. A link for that will also be presented later. So let's get this party started with our first round of amazing demonstrations.
Let's make a big cloud. Watching clouds is always fun, but standing in a cloud is even better. How can I make a big cloud? I have a container here that has liquid nitrogen, basically liquefied air. It is at temperature that is 400 Fahrenheit, colder than temperature of your skin. So what will happen if I pour liquid nitrogen in hot water that I have in this pot? Are you ready? Water vapor condenses at low temperature, turns into water droplets, And we have a cloud. How can you make a cloud at home? Our next video will explain it.
On small scales, we can create our own clouds using this little bottle. First things first, our demonstrator will add rubbing alcohol to this bottle. Imagine the air in the bottle as our atmosphere and the alcohol as Earth's water. We're going to pressurize the bottle by pumping air into it with this bike pump. Watch how with the simple power of pressure, we can evaporate the alcohol into a cloud and condense it again. Making clouds is quite the workout. Once we've added enough air, we can cause a sudden pressure drop by popping the stopper off. There it is, a cloud in a bottle. The sudden pressure change caused the alcohol to quickly evaporate. This causes rapid cooling, transforming the alcohol into a cloud. Now, as we pressurize the bottle again, we see the cloud slowly precipitate back into a liquid alcohol at the bottom of the bottle. We can continue the cycle as many times as we want. If we pop the stopper again, the cloud comes back. This is a lot like how the real water cycle works. As long as water stays on planet Earth, the cycle keeps going wherever there is a change in pressure.
I would usually ask for a drum roll to introduce the next speaker, but his demonstration will do the talking. Now we will be moving on to Jeffrey and his crushing drum experiment.
Okay, so over here we have a steel drum. This is normally used to transfer oil from location to location. But today, I want to show you guys that this steel drum is actually not that much more different from an ordinary plastic water bottle. The way that I'll be doing so is by using this vacuum pump. Let me turn it on real quick. Can you guys still hear me? Good to go. Okay, so the vacuum pump will be taking out all the air out of the steel drum. This process normally takes from 3 to 4 minutes, give and take. But before we continue on about the physical demonstration, it's been a long day for me. Oh, that's not it. It's been a long day for me, and I need a drink of water real quick. Oh, this is new, right? We've all done this before. But what happened here? Why did the water bottle contract and shrivel up like it did? Well, simply put, it's because of the atmosphere that surrounds us. The atmosphere is filled with a lot of stuff, mostly nitrogen and oxygen. But again, it's a lot of stuff. And all that stuff acts a huge amount of force on our bodies, at around 15 pounds per square inch. That's called the atmospheric pressure. It is so strong that when I took out all the water and all the air out of this plastic water bottle, this is what happened. Okay? So, what would happen, let's say for example, actually let me correct myself. Why do we actually withstand this pressure very nicely? Well, simply put, it's because of evolutionary processes. Our bodies are filled with water, air, blood, muscles, bones, so on. All of this stuff within our bodies actually apply a force counteractive to the atmospheric pressure, to the point where we reach the equilibrium point. This means basically that we feel a lot of nothing. But doing this to a water bottle is not that impressive. But doing that to a steel drum may be something that you can see as shocking. For the rest of the time that we have here, we just have to wait and see if this thing will actually work. Well, there you have it. It did work. And this thing actually surprised me. It almost sent me flying, to be honest with you. But I'll leave all the flying to our next presenters, Nicole and Chelsea, with their flying mirror and floating head demonstration.
Welcome to the jungle, the physics jungle. Here in our zoo, we have many animals, but only one place for them all. Elephants and giraffes are huge. Can we store all of these animals in this dewar?
They all fit, but something's not quite right. Good news, everyone. The animals all came back. Let's explain what happened with our balloon. Our balloon is too large to fit in this thermos, but we're able to shrink the balloon using liquid nitrogen. When the air inside the balloon cools, it takes up less space. Now watch as the balloon warms and expands back to its original size when removed from the liquid nitrogen. No animals were harmed in the making of this video, only balloons.
Did you know that most magicians actually use physics for their magic tricks? They sometimes use a very specific area called optics. This may look like any old table, but in reality, it's actually an optical illusion.
Boo! Did I scare you? For this demonstration, we're going to teach you guys the secret behind magicians' most famous magic tricks, like how they can make heads float on tables.
Or how I can look like I'm flying. Look, Nicole, I'm really flying.
Wow, Chelsea, that's so cool. These tricks are actually very simple. It's just mirrors placed in just the right position.
This mirror is placed at a 45-degree angle, which reflects this box to make it look like both my legs are floating.
We've done the same thing here with this table, see? Hello! Once you know how to use mirrors to bounce light, you can make 100 different demonstrations just like this.
And once you learn the magic behind optics, you can bend light to change how you see the world. And there's even more fun stuff we can do with physics. With a few clever tricks, you can even see sound. And thanks to our next presenters, Adrian and Josh, they'll show you how to do just that.
Hello, this is a Rubens tube, and it's going to show us how sound works. Now, the tube itself is just an empty hollow metal cylinder. At this end, we have it completely closed off so that nothing can pass in or out. But all along the top of the tube, there are little holes that will allow air to pass in or out. And at this end over here, we have a membrane or diaphragm, which doesn't allow air in or out, but it will allow vibrations to come into the tube. Okay. Now, there's nothing special inside the tube. There's no special structure, no special chemicals, except for the fact that we'll be filling it with propane gas. Now, as the gas fills inside the tube, eventually what we can get are streams of propane gas coming out of the holes along the top. As these streams become more stable, we can light it on fire. All right. Now, how can we use this to study how sound works? Well, back over there at the end with the membrane or diaphragm, we have a speaker. Now, this is just a normal speaker, ordinary speaker, just like any kind of speaker that you might plug into your computer or a home audio system. Okay. And into this speaker, we have a keyboard. So basically, anything that gets played in from this keyboard into the speaker will pass into the diaphragm and vibrate the membrane in the diaphragm. Okay. And when we do that, this will happen. Okay, so we get a wave pattern forming along the tube. So why is that? Well, this is how sound works. So sound is a pressure wave. Basically, in that speaker, there is a metal cone. And whenever frequencies are passed from the keyboard into the speaker, that cone vibrates and pushes the air in and out. When that happens, it causes the air to become more and less dense over and over and over. As this pressure wave travels down the tube, that means it will force more or less air out of the holes along the top, or in this case, flaming gas. So why do the wave patterns look different, and why do different sounds sound different to us? Well, that's because every sound has a wave pattern, and in particular, it has a wavelength which we can visualize with the tube. So you notice that low-sounding noises have long wavelengths or very low frequencies. On the other hand, high-pitched sounds have very high frequencies or very short wavelengths. Okay? And now our ears and brain interpret the oscillations and vibrations in the air as different noises and notes, but the Rubens tube allows us to actually visualize what those look like.
So friction is both a force that we love and hate. And we hate it because if I slide these books across the table, they're eventually going to stop. I would really like it if nature would allow something I push just to keep on moving forever, not drain energy from the system. But unfortunately, that's not going to happen. But friction is also very useful. It's the only reason I'm able to walk around. If it wasn't for friction, I would fall all over the place because there would be nothing allowing me to push myself across the ground. So, friction both useful and annoying. So, if we look at two sheets of paper though, if I put two sheets of paper on top of each other, the friction force between the two of them is practically negligible. I can go ahead and pull these pages apart without any problem. But if I take two books and I interweave the pages, this friction force suddenly gets a lot bigger. And it's really hard to pull. So you can get a friend and you can try to do a tug of war. And you notice that no matter how hard we pull, the books just won't come apart. So, if you ever want to fight your friend, or just give him a little pull, go ahead and interweave some phone books. Anyway, we hope you enjoy the festival.
Hello. So here I have the Earth and the Moon, or at least inflatable ball versions of them. It's a little demonstration we're going to show you about the Moon's orbit around the Earth. So, you saw this Earth and Moon fly, but how did we do it? Was it magic? Did we use wires over them? No, it was physics. It was through a thing called the Bernoulli effect. So what is the Bernoulli effect? The Bernoulli effect is when we go ahead and have a stream of fast-moving air. When this fast-moving air is moving, it creates an area of low pressure in that stream. This leaf blower here can make a stream of fast-moving air by simply blowing it forward. When I have a ball, like this little inflatable one here, and I put it in this stream of air, the outside still air that's not moving forms high-pressure walls, locking it into place along the length of that stream. This high-pressure walls can actually offset gravity a little bit, allowing me to tilt it over, up to a point. At a certain point, the force of gravity actually outweighs the force from these high-pressure walls, and the ball will tip. Let's demonstrate. Want to try the Bernoulli effect for yourself at home? Well, you don't need fancy balls or a really big, powerful leaf blower. You can do it with a simple leaf blower, some toilet paper, and a broomstick. So when I blow a stream of air over the edge of this toilet paper, this toilet paper is going to get sucked up into this low pressure stream and follow along with it. Then I can make it go everywhere I want just by pointing the stream left, right, up, or down. So let's do it large scale.
Let's roll!
Howdy! In this demonstration, we have an aluminum pendulum and a giant magnet. Is aluminum magnetic? We can easily find out by using an aluminum soda can and a simple magnet. So we can clearly see that aluminum is not magnetic. So do you think it would be a good idea if I inserted my leg right in the path of this aluminum pendulum? Let's find out. But I can't watch. So we can see that my leg is still intact. But why? The reason why is as the aluminum pendulum goes through the magnet, there's a change in the magnetic field in the pendulum. This change in the magnetic pendulum creates a current, which we call eddy currents. These eddy currents generate its own magnetic field that oppose that of the magnet. What do you think would happen if we added slits to the pendulum? Let's find out. I'm glad my leg wasn't there because the reason why it didn't work this time was because of the slits. The slits didn't allow the eddy currents to flow within the pendulum, which didn't create the magnetic field that opposed that of the magnet. This demonstration is an example of Lenz's law and of magnetic braking. I hope you enjoyed this demonstration.
Have you ever wanted to go for a dry swimming session but didn't want to brave the cold waters? Well, do I have a solution for you. In this demonstration, I will show you how to go for a dry swimming session. In this plastic container, we have filled it with very, very fine sand. And as you might know, when you put stuff on top of sand, it just kind of stays there. But if I go ahead and turn this valve, something amazing is going to happen. 3, 2, 1. The sand becomes liquid. So I can have things float. I can have things sink, just like they would in water. But why does this happen? So that's the real question. Well, what we have is a really interesting use of Bernoulli's principle. So just like before what you saw with the levitating bulb, what we've done is we've pumped air in from the bottom of this container. That creates an upward force on each sand particle, which is counterbalanced by the force of gravity. This allows each sand particle to essentially float in place, making the sand become a liquid. Now, this is a lot of fun for me, but this might be hard for you to do at home. But we will have a lot of other demonstrations to show you that you can do in the comfort of your own house. But next up, we're going to go to our famous Foucault pendulum. I hope you enjoy the festival.
Behold, the Texas A&M Foucault pendulum. The pendulum stands 7 stories tall, and the mass at the end weighs 400 pounds. That's 400 bags of marshmallows. So why did we build this thing, and why do people spend hours observing its motion? We all know the Earth rotates. The sun rises and sets every day. The stars rotate at night. But the first visual demonstration of the Earth's rotation was Foucault's pendulum, created in 1851 by French scientist Léon Foucault. To the Lego man, it seems the pendulum rotates and the Earth stays still. However, as we can see, the Earth actually rotates under the pendulum. So, on the North Pole, in exactly 24 hours, the pendulum will seem to make a complete rotation. Now let's talk about what happens on the equator. We can see that no matter what direction we start the pendulum in, it will not seem to rotate. It's rotating with the Earth. Here's a model of the pendulum's path at Earth's North Pole, equator, and somewhere in between these two extremes. Texas A&M's Foucault pendulum is at a latitude of 30.6 degrees. Our model tells us that the pendulum will take 47 hours, 7 minutes, and 11 seconds to make it all the way around. Let's see if it's right. And indeed, physics wins again! Time to celebrate! Come visit us at Texas A&M and see our pendulum, and you can personally observe this effect over the course of 47 hours.
Hello there! Today we are going to talk about a stacking block problem or layer tower. So as you see, we have some wooden blocks here. As I want to stack them on top of each other, I can do this forever. I can go any height, I can add more blocks and everything. But what if I want to put them a little bit off balance? So for example, if I want to have something more curved, not just going up. So let's see how far it takes that I can push this block without it falling. Okay, still good. Oh, it fell. So what is about these blocks? These are geometrically very symmetric, meaning that the central mass, central gravity is right in the middle. As long as the center of mass of the second block is supported by the first block, it's not going to fall. See? It's still there, still there, still there. But as soon as the center of mass is not supported, the torque of gravity causes this to rotate and fall. So let's say we push it a little bit back and the center of gravity now is on top of the first block. Let's add another block and see what happens. Okay, we are putting the other block, push it, push it, push it. Oh, so close. Okay, now it stays. So as long as the center of mass of the combination of these blocks is supported, they are not going to fall. So if I continue this with another block, we are going to see that the length of the overhang for the first block is 1/2, the second one is 1/4, 1/6, 1/8, and 1/10, 1/12, and so on and so forth. So this can go forever without this one to get to being 0, right? So this never gets 0, it gets smaller and smaller and smaller as long as the center of mass of the combination is supported. So here we have a made tower layer. So it's already made, and you can see that this size that is overhanging is 1/2, 1/4, 1/6, 1/8, and so on and so forth. So this is basically a mathematical series, and this is not 0. So if you want, you can continue this for as long as you want till this overhang gets further and further from the table without falling.
Howdy, everybody. I hope you guys are enjoying the physics festival so far. Some of the demonstrations you've seen thus far might make you think that you need big contraptions or expensive materials to do physics demonstrations, but that's just not the case. All I have here is a potato and a straw. What do you guys think is going to happen when I stab this potato with a straw? Let's see. It breaks. Of course it breaks, because this potato's pretty dense. But now let's see what happens when I take the straw and put my thumb over it. It went through so easy. Why do we think that is? Well, when I put my thumb over this straw, I've trapped all of the air inside the straw. Now whenever I stab the potato, oh, sorry, I stabbed it a little too hard. Let's try another one. Now when I stab the potato, it goes through so easy because I've created pressure in the straw that keeps it from bending.
Hey, Nicole.
Hey, Chelsea.
Are you doing potato physics?
Yeah, of course I'm doing potato physics.
I love potato physics. Did you know you can even show Newton's first law with just a potato?
Hey, I know Newton's first law. That's that all objects have inertia and you have to apply a force to them to change their motion.
That's exactly right. What do you think will happen when I hit this knife with this hammer?
I don't know. That's a really good question.
What do you guys think? Put your answers in the chat, and the first person to get it right gets a prize.
Let's see.
You think it might fall? Maybe you should put your hands underneath just in case.
Let's see.
All right, has everyone put their answers in? Let's see what happens.
It's going up the knife. That is the last thing I expected to happen.
Yep, this potato is heavy, which means it has inertia, and the frictional force of this knife isn't enough to make it move. So as the knife moves down, the potato moves up the knife.
That's so cool. As you guys can see, physics is so much fun, and you don't even need expensive materials to learn about it. I hope this has really lit a fire under me, and I hope that Dawson with methane bubbles up next will do the same for you guys.
So far, we've seen a lot of really cool demos, but we're here to bring the fire. So Sean over here is going to explain how it's done.
We start with a methane canister full of methane gas, which is fed through this copper tube into a bucket of soap and water.
So what's going to happen is this bucket is going to be filled with bubbles, but these bubbles are filled with methane. Now methane is lighter than air, so as these bubbles fill up, they're going to rise up, but because they're lighter and less dense than air, they're going to start to form a nice pillar. Now, you may also know that methane is a very flammable gas. So would it be a smart idea for me to light this pillar of bubbles on fire? Let's find out. One, two, three. Wow, wasn't that cool? Or should I say hot? Now, I know you can't feel this at home, but this pillar was really, really, really warm. And I'm curious, would it be a good idea for me to, say, light this bubbles on my hand? Well, just in case it's not a good idea, Sean over here has a fire extinguisher just to make sure I'm safe. So let's go ahead and turn those bubbles back on. We're gonna get a nice couple of bubbles made, and I'm gonna go ahead and grab some of them. All right. Ready? 3, 2, 1. Ah! No, I'm fine. So, why am I fine though? That gas is really hot when it's burned. So, how did my hand stay okay? Well, what you didn't notice necessarily is that when I stuck my hand into the bubbles, I didn't just pick up the bubbles. I actually stuck my hand into the water. And when I lit the bubbles on fire, that little layer of water that was around my hand essentially protected my hand by creating a nice vapor layer which was turned to steam. So I was protected for an instant. So I'll show you one more time. So I stick my hand, get some bubbles, and burn the bubbles while not hurting my hand. So just remember, do not try this at home, and have a great time at the festival.
Wow, you've all been asking wonderful questions. Let's get some of those answered. Our first expert is Adrian Thompson.
Hey, thanks very much, Morgan. So I wanted to start the Q&A off with what I think is a really interesting question. Yoon Park asks, can you freeze lightning? And I think this is the kind of question that I ask myself all the time, these crazy what ifs. And I think the answer is no, right? And it's for a very fundamental reason. So lightning, along with other forms of electricity, is about the movement of charges over space. So in order to freeze something, that means that you're actually stopping the microscopic movements of all the atoms and molecules in that substance. So unlike materials like water or metals or other substances that you can actually freeze, lightning is something that fundamentally has to be moving at a microscopic scale. So I think that's a really great question.
I see. Okay. Well, thank you so much. We've got another expert coming up here in just a moment. Now we have Dr. Alexei Belyanov. Welcome.
Hi, everyone. So there is a group of similar questions, and all of them boil down to one. How high is atmospheric pressure? For example, Alejandro Garcia is asking, would taking out all the contents of any container lead to it being crushed? And the answer is, well, it depends on how strong your pump is, because imagine atmospheric pressure is roughly 15 pounds per square inch. So this coin already, like a quarter, holds about 2 pounds of weight of the total column of air. So my cell phone would be like experiencing 150 pounds weight of the column of air above it. So if you really suck all air out of your container, imagine it will experience more than 100 pounds of pressure. So that's probably enough to crush almost anything. However, of course, you can't really suck all air out. There is still some pressure of air left inside, and therefore it really depends on how strong your vacuum pump is. And you don't even need a vacuum pump to experiment with atmospheric pressure. Imagine the suction cup hook. All it does is exploits the atmospheric pressure. When you stick it to the wall, the suction cup, then it basically pushes the air from inside, and therefore there will be much less pressure inside than outside, and this will hold your suction cup hook in place. So yeah, it's pretty strong if you can play with this.
Wow, thank you. That really reminds me of submarines, kind of in the inverse sense. We're not sucking air out, we're just crushing it from the outside. Very interesting. For our next question, we've got Dr. Dawson.
Hi, so Brenna Allen, I hope I pronounced your name correctly, asked, if the fire on my hand stayed lit for longer, wouldn't the water eventually go away? And the answer is yes. So this is called the Leidenfrost effect, and this protective layer of vapor that goes on my hand only exists for a very short period of time. That's why we use methane as the gas, because it burns very rapidly when I light it. So the vapor layer sits around just for a short second, protecting me. But if that flame was able to sit around for longer, I would be in big trouble. And I recommend not trying to experiment with this at home.
Yes, please. Fire is dangerous. Yeah, don't play with that. Thank you so much, Dawson. And next we have Josh Winchell.
Hello, everyone. I believe it was Madison asked a good question about the Rubens tube with the dancing fire. What happens if you play multiple notes at once? In that case, you get multiple waves overlapping, and they will all just add up. So, in theory, if you had a really precisely made Rubens tube and perhaps an infinite supply of gas, you could play a really low note with really long wavelengths and a really high note with really small wavelengths, and you would end up with these like really long extra bumpy waves. There is a limit to how much we can do though, and furthermore, not every note has the exact wavelength to set up nicely in our Rubens tube, but in theory, you could see this perfect combination of waves with any combination of notes.
Thank you so much. And for our next question, we have Adrian Thompson again.
So I wanted to also bring in another question, which may be not super physics related, but I thought it was really interesting. Dino Girl asks, are there any organisms that can survive in liquid nitrogen in regards to our liquid nitrogen experiment? So that's not directly physics related, but it's still really interesting. So there are apparently. So there are these organisms called tardigrades, or water bears, that can actually survive in super, super cold environments. Now, I don't know the reason for this exactly. I'd be really interested to know. But I know that one of the difficulties for organisms surviving in cold environments is not just their ability to regulate their own body temperature, but also to prevent themselves from drying out, right? So you want to, if you're an organism, you're trying to survive, you need water to actually be able to keep all those chemical processes inside your body going.
Very cool. Thank you so much, Adrian.
Yeah, thank you.
And next we have Josh Winchell again for our next question. Welcome back.
Hey. So Elliot asks, referring to the demonstration Dawson did, are there other liquids you could coat your hand with to handle fire safely? In theory, yes, the physics works for other things. The issue is how quickly those other liquids would change their temperature and therefore pass that extremely hot temperature onto you. Water happens to be a pretty good liquid to use here. I mean, partly because it's really easy to come across, but also water has a relatively high specific heat. Other liquids might evaporate faster and pass that fire onto you faster, so best not experiment too much.
So here's an interesting question on that. Is there a way to coat your hand in some sort of wick or cloth to hold whatever you're trying to vaporize to protect yourself?
Again, like with liquids, if that, well, in essence, of course, just is that wick or whatever really fire resistant, or is it going to itself burn up and then pass it on to you?
I see. All right, well, thank you so much. We have Adrian here again.
So another question from Alejandro Garcia about the Rubens tube. So he asks, if you had louder speakers, would that mean larger pressure waves inside the tube? I think that's interesting. So yes, you would have larger pressure waves. And what that means is that the pressure inside the tube would actually be higher, right? Or rather, the variation inside the tube in terms of the variation of pressure would be larger. So if you're thinking about the wave pattern inside the tube, there are points where the pressure is constant and not changing too much. And then there's other points where the pressure is varying according to the wave pattern. And those points where the pressure is varying, those would have a larger amplitude in terms of the amount of pressure that you're actually experiencing at those points. Yeah.
Very interesting.
Yeah, and in addition to that, I can also comment that in addition to having louder speakers, which means more power that you're transmitting down the tube, you can also have larger flames coming out of the top further down the tube. So another thing that you may have noticed with the tube is that the waves near the beginning of the tube were really high and the waves at the end were very low. The height of the flames were very low. And so with a louder speaker, that means that you're not going to lose, or rather that you can get more power transmitted all the way down to the end of the tube, instead of having that kind of loss, that fall off as you're going towards the end of the tube. So there's more power transmitted essentially.
That's really neat. I'm just trying to imagine like an organ playing with fire spewing from it. Very cool, very cool.
Yeah.
And next, and probably our final question, is going to be answered by Dr. Dawson once more.
So, Callie Hayden asked about the heat that I felt on my hand. Like, how hot did it feel? Was it about with the water and everything? So, I can say this: it feels very, very warm, but it only lasts for a second or two. So it's not as hot as like touching like a hot pan and immediately feeling the heat. It's really just a really quick increase in warmth because that vapor layer is created. So you feel some warmth show up, and it's definitely it's not unpleasant, honestly. It's just a little bit extra warmth there that just sits around for about a second or two, and then it's really gone. So it seems more. The first time I tried it, I was very uncomfortable trying it. I'll be honest, because lighting your hand on fire is a little scary to do the first time. But I've done this so many times at this point that it's honestly even more fun than scary. But the one thing that I would say is that when I made that big pillar of bubbles and I lit that on fire, that one you can really, really feel the heat even behind the shield. That's one that you really, really have to take care for, and that's why we put this little plastic barrier around it to protect everybody.
Awesome, awesome. And as another reminder, in case I didn't make my point very clear earlier, don't light your hands on fire. Don't light anything on fire. Thanks. All right, well, thank you, Dawson. Those demonstrations were really something. We'll have more of those in just a moment. Remember, ask physics questions in the chat. We've got plenty of experts, and we would love to have them answered for you. And remember, subscribe to our channel for a chance to have your name featured on the screen. So with that, let's also not forget to mention our wonderful donors again. Running the Physics Festival each year would be impossible without the generous support of our amazing Aggie community and fans. Thank you, Halliburton, for your generous contributions to help the festival puzzle and inspire thousands of people across the globe. We also want to thank Colonel Hal Shade, class of '67, for making this year's festival possible. Last but not least, we are so thankful for the support from our donors to our crowdfunding campaign, which raised over $5,000. To all of our donors, this is really impressive. Thank you so very much. We'll be back in just a moment, so this is a great chance to take a quick break and prepare for our next speaker.
It is my immense pleasure and honor to introduce our very special guest, Professor Dr. Nancy Currie-Gregg. Nancy is a true national hero. She served our nation as a military pilot, as an astronaut. She spent, can you imagine, more than 6 months away from the ground, either in a cockpit of a military aircraft or far, far away in space. Nancy, please, the floor is yours.
Oh, thank you so much. Thanks for the great welcome. And it's sure great to be back speaking at the Physics and Engineering Festival here in the campus of Texas A&M University. I'm actually in my campus office right now. And gosh, I sure wish I could walk across campus and see all of you in person, but we're all doing the best we can in these pretty challenging times. So I really want to thank the festival organizers for providing this opportunity for students literally potentially around the world to tie in and to get a little glimpse into what human spaceflight is all about. As was mentioned, I have 1,000 hours in space, and all astronauts like to start out by talking about their own missions so that you know I've actually been there, done that. And I was selected as an astronaut back in 1990. I was fairly young, one of the younger astronauts selected, just had turned 30 years old, just had a baby, literally like 6 months prior. And I didn't have a very long wait. At that time, we were flying shuttle missions on a fairly regular basis, sometimes 5, 6, even 7 missions a year. And my first mission was in 1993. And when we did simulations of this mission later on, it was called the Dream Flight. And it was called the Dream Flight because we had elements of doing experiments in space. We flew the first flight of a SpaceHab module, which was a pressurized module that you could access from the shuttle. And we had a whole myriad of experience, from biomedical experiments to some of the things that were predecessors of systems that ultimately flew on the International Space Station. In 1995, again, not a very long wait for my second flight, we deployed a tracking and data relay communication satellite. So that satellite gave us the capability to talk from the shuttle up to the satellite down to the ground. And interesting to note, it actually was a replacement for the satellite that was lost during the Challenger mission. And so that was very special to us as a crew to see that mission come to its realization. All missions are good missions, but some are better than others. And my third mission definitely fell in that category. I still don't know how I was selected for this mission, but I got a call one day from the chief of the astronaut office, who turned out to be our commander on the flight. And he said, "How would you like to help us build the International Space Station? Take up the first piece, made it to the first Russian piece, and literally put out the building block of the International Space Station." And when I came to work at NASA, even before I was an astronaut in 1987, people had been working on the space station program for almost a decade. And to be able to be part of the crew that was just a little tiny piece in putting those elements together, 215 miles up in space, was really one of the highlights of my professional career. And then my last mission, again, all missions are good missions, some are better than others. And I actually got a choice on my last mission. They asked me, would I like to go back to the space station or what I like to service, the Hubble Space Telescope. And I don't know about you, but I am a huge fan of the Hubble Space Telescope. And I just jumped at that opportunity because I actually saw it as a brand new astronaut when it was still on the ground before it ever launched. Now, in retrospect, of which I would have paid a little bit more attention when they were talking to us about the Hubble Space Telescope when we were touring around. I had no idea that someday I might be put on a crew and asked to go service it. But fantastic mission. And on all 4 of my missions, I was a robotic arm operator. You see the robotic arm being used quite a bit in a lot of these photos. This is me at the robotic workstation. And this is me. That's the actual configuration, because at launch, you're laying on your back. The acceleration vector goes through your chest as you launch up into the sky. So what is the International Space Station? It's truly an international partnership several hundred miles up in space. It is one of the most ambitious engineering programs ever undertaken. It took 5 different space agencies that represent over 15 countries around the world. And it required over 35 space shuttle missions dedicated to take up every piece, albeit not the very first piece, not the very first Russian segment that was launched on an unmanned rocket, but all the other elements we took up in the shuttle payload bay, which is 60 feet long, 15 feet across. And then we assembled the space station on orbit, and we used robotic arms. We used our spacewalking crew members, what we call EVA, extravehicular activity. And so it was an extremely ambitious and somewhat lengthy period of time to build this fantastic orbiting laboratory 215 miles above the Earth. So how do you achieve very, very bold goals? You do it one step at a time. I'm often asked, how did I end up being an astronaut? And I would say one step at a time. And in fact, I use the analogy of a ladder. And I climbed up each rung knowing that that might be as high as I get. But I had to clear that first rung, and then the second one, and then the third one, if my goal was to literally reach for the stars. And so that's what I would implore you to do, that look at it as a path forward, and you want to have a passion for what you do, because you don't know what rung you might stay on for a whole host of reasons, many of which may be beyond your control. And so I started out my career as a military helicopter pilot. If that's all I'd done in my career, I would have been thrilled. I loved flying helicopters. I love serving our nation in the military. But certainly, I continued to improve myself over time with the hopes that I could keep climbing up that ladder and ultimately fly in space. I want to also say, especially for the teachers that might be on today, that while it might have been an Astrovan that drove us out to the launch pad, in my mind, I was carried to the launch pad on the shoulders of my teachers. Neither one of my parents graduated from high school. And it didn't take long through my education before my teachers became my inspiration and my guidance. And when I launched on that first flight, sitting right next to my parents in a very small reserve family area were my high school math, biology, and chemistry teachers, because they helped me get there. So don't ever forget the impact that you as teachers have on young people with goals that may seem so bold in their ambition that they're unachievable. Because thankfully, we live in a nation where anything is possible, and that everybody gets an equal opportunity to succeed. So literally, we went from these first 2 pieces. This is the first Russian segment called the functional cargo block. This is the first US segment called the node. And you can see these ports all around. So there's 4 ports around, 1 port here and 1 port here. And that's how we built up the space station, by connecting in space additional modules and building it up. Till finally, at assembly complete, it truly is the brightest star in the night sky. If you've never seen the space station fly over, you can go to ISS sightings on the NASA website. And I still do that today. And it still takes my breath away, because to look up at the night sky and know I had just a teeny little part in that fantastic engineering feat in orbiting laboratory is very, very special. So what I'd like to do now is just to show you a very short clip about that mission, and then we'll talk a little bit more about it. So that was in 1998, so just a few years ago. We celebrated our 20th anniversary. So this is the Russian spacecraft launching out of Baikonur, and under that big black shroud at the top is Zarya, otherwise known as functional cargo, first Russian segment. So this was launched on an unmanned rocket, and this is when we first saw it in space. What a fantastic sight. And so 2 weeks later, it was our turn to launch. And this is us in space, rendezvousing with, grappling the functional cargo block. It had a grapple fixture on the side that you'll see here shortly, and then mating it to the first US segment, which was very difficult. We'll talk a little bit more about that. And now we had to do a series of 3 spacewalks to make all the electrical connectors, fluid connectors. You can see us using robotic arms. Here they are here in the hatch on that plane. Here are them top board and right up for access to public. This is the international. Besides the U.S. segment, even though it's a small segment in the U.S., still very large, very small. And we started putting working up an introduction of completely different. And then our mission was over. Back away by firing what we saw. The start of the International Space Station. 35 missions later, this is what it looks like today. Currently, as of yesterday, 10 people on board the space station, 215 miles up, orbiting the Earth. Again, just a absolutely fantastic opportunity to be on this. Now, I mentioned the somewhat difficult maneuver of, first of all, grappling this very large spacecraft out in free space. And if you don't know, a rendezvous is basically flying formation on something, except when we're orbiting the Earth 215 miles up, we're going 5 miles a second. That's 17,500 miles an hour. So 5 miles a second, and you're trying to basically match exactly the speed of the shuttle with the speed of the other spacecraft, so you can reach out with the robotic arm and grab it. And we only had 90 seconds to do that. And I won't get into all the details of orbital mechanics, but basically you can see that this spacecraft is slightly, relatively speaking, above us. Actually, it was below us because we were actually pointed down towards the Earth. And just like on a racetrack, if you run on the inside circle, and ran the exact same speed as your classmates on the outside circle, you're always going to win the race, right? Because relatively speaking, to cover a whole lap, because you're covering less distance, your speed is greater. And the same thing happens when you're rendezvousing with a vehicle. So that's why we only have 90 seconds, because that arm is only 50 feet long. And pretty soon, orbital mechanics will cause it to drift up and away, and then we no longer have reach with the arm. So the first major event was grab that thing. Big sigh of relief when we did, but now we got to put them together. And the tolerance of mating this element that was developed, designed, and manufactured in Russia, and this element developed, designed, and manufactured in the US, was plus or minus 2 inches and 2 degrees. If we were more than 2 inches offset, it wouldn't have mated properly. And so you can see I've got some cameras here, and I'm going to talk a little bit later about a system we use to determine what that relative offset was. But you can tell from this view here, if I had to guess when these things were perfectly aligned within 2 degrees and 2 inches, that'd be a pretty difficult task. So we spent a lot of time in virtual reality labs, in simulators, training for that task. Now, once everything was mated, at least according to Jerry Ross and Jim Newman, who are spacewalking crew members, they said, this is when the real mission starts, because they had to do a series of 3 spacewalks, and you can see all the electrical connectors here. And of course, those electrical connectors now need to be mated between the 2 elements to provide power and data and so forth. They also, if you can see these gold things right here, these are handrails. So as our spacewalking crew members are outside, and if they're not on the end of the arm, like you can see Jim here, not on the end of the arm, then to get around, he has to grab these handholds and go from handhold to handhold to get around the exterior of the space station. And quite frankly, we didn't have the clearance in the payload bay. We took up all the payload bay with this module. And so once we got up there, we had to install these supplemental pieces of equipment like the handrails. Once the spacewalks were done, it was time to go inside. Now, this is the commander, Colonel Bob Cabana, who was a colonel in the United States Marine Corps. And this is Sergei Krikalev. Sergei, to this day, is one of the most experienced cosmonauts in Russia. He spent time on the space station Mir. He was on the first crew to assemble the space station along with us, and he was on the first crew to live on board the space station. I learned so much from Sergei. It was just a dream come true to fly with a cosmonaut who was so experienced at flying in space. And so they didn't tell us, but what their agreement was when they went in to the space station, they went in side by side, and they wanted to show the unification of the United States of America and the Russian government working collaboratively in space for peaceful reasons. And I must tell you that Bob was in the Marine Corps. Our pilot, C.J. Sturkow, was in the Marine Corps. Jerry Ross, a colonel in the United States Air Force. Myself, a colonel in the United States Army. When we had all come into the military service, we did not have an amicable relationship with the Russians. And so now suddenly we're in a Russian factory and in Moscow, staying and learning everything about their systems. And what a joy it was to have transitioned from worrying about, being attacked by the Russian military forces to working collaboratively on a peaceful endeavor, one of the most boldest and outrageous engineering feats ever accomplished. And that really resonated with me personally, and I think all of us. As I mentioned, the US node is one of the smallest segments of the space station, but compared to the shuttle, wow, it was a fantastic amount of space. Remember, in a microgravity environment, and I'm in footloops here, if I let go, I could float anywhere I wanted, to the ceiling, to the floor. I can sleep on the wall. I can sleep upside down. And in fact, to play a game with me, 2 of my crewmates took me, positioned me right in the middle of the module, made sure I wasn't moving in any direction and let go of me. And I was literally kind of stranded in the US segment. And I was trying to swim, and I was trying to make enough air current so it would push me towards one side or the other. And unbeknownst to me, they sent all this video, of course, to the ground to make fun of me. Now, this is the Russian segment. And the first thing you notice is, completely different architecture, but very useful, designed for living and operating in space. And a couple things about it. One of the things that you notice is the relative ceiling has lighting on it. Here in the US node, the lighting is fairly constant around all the sides of the module. So if I've got my head upside down and I'm installing that communication system and I pull my head out, I can't tell whether I'm upside down or right side up, quite frankly, because I'm not sensing it in what we call our vestibular system. Our vestibular system is our inner ear. We have utrickles which are kind of like little hair cells. And as the fluid passes across, it gives us a sense of linear acceleration. And then we have 3 semicircular canals that are located at 90-degree angles to one another. They also have fluid in them. So as I tumble, if I were to tumble here on Earth, I would feel that tumbling sensation because my semicircular canals, that fluid in it, would be accelerated. And that would give me that sense. But in a microgravity environment, that fluid is not accelerated, it's stagnant. So you have no idea from that sense, that vestibular sense, that you're upside down. So what tells us if I'm upside down? Well, this label that was put on the ground that says to the cupola, that label gives me some sense, but it's also somewhat provocative. And at the end, I'm going to talk about some real challenges in human spaceflight, which is primarily the effect on the human body and what we know and what we still don't know about those effects. So for one thing, you never get lost in the Russian module. The other thing, and it's hard to tell, but all of these panels are Velcro. And Velcro is an astronaut's best friend. Because if I let go of my book, and in fact, you can see my book, this is Velcro stripes on my pants. My book is Velcro to my pants, because if I let go of it, it's going to float off somewhere. And we have lost things on the space station, and they've gotten behind panels, and they floated away from us. And in fact, when Sergey and I were doing an operation, we both have power tools, and we were disconnecting over 200 non-captive bolts and washers that were holding these panels on. Now, the reason for that is when you launch into space, there's a whole lot of vibration. And so those panels have to be secured very well. But once you're up in space, very little sources of vibration. And so it's just like in your house, you don't want to have to pull out a power tool every time you go into your cabinet in the kitchen. And so we wanted to remove all those. So they were non-captive for a reason. They were intended to be removed. So when I took them off, I used one of our trash bags that we use during our spacewalks. And it has a self-closing mechanism. And so I could push a bolt in and it would close up and they'd all stay in the bag. And Sergey, who had a lot more experience than me, said, you don't need anything that exotic. I'm going to use a baggie. But what he didn't plan on is it only could hold about 199. And when he put number 200 in, the bag burst. And you can imagine, I looked up, I heard him say, uh-oh. And I looked up and there was just a sea of bolts and washers and nuts. Now I started to get a little bit nervous because I thought the ground saw it. And Sergey says, no problem. We wait about an hour. We go to the filter. And the filtered air, the airflow is going to take all of those bolts and washers and nuts, and they're going to be right there in front of us on the filter. And that's exactly what happened. Now, one of the things about being an astronaut is we play a game. It's not really a game because it's a game of very high stakes, but we play a game of what if? What if things don't go according to plan? Because I will tell you, where our engineers are extremely smart and the people who train us for these missions are extremely smart. And they try to postulate every potential thing that could go wrong in a mission. But I will tell you, on all 4 of my missions, we had things that went wrong that weren't in the plan. The first one, I will tell you, we had concerns about, but we really didn't have a good alternate approach because there was a decision made early on that in order to mate the elements on the space station within those very tight tolerances, plus minus 2 degrees, 2 inches, that we needed to use a vision-based system to tell us what our relative offsets are. So you can see here, we've got these dots all over the Russian segment and the US segment. And by looking at a series of dots on one element and a series of dots on another element, now we can use math to compute our relative offset, whether that's in what we call X, Y, and Z, which is our translation. So X is in and out, and Y is to the side, and Z is up and down, or whether it's in pitch or yaw or roll. So it would give us that. But here's the problem. This system was designed, developed, and tested here on Earth. And the thing that's one of the most unique things about flying in space is the dynamic lighting conditions that you encounter because you're flying around the Earth every 90 minutes. So 45 minutes you're in daylight, then you have a sunset, 45 minutes in darkness, sunrise, and repeats over and over again. And so when the lighting is changing so rapidly, it creates glare and it creates shadows. So you've got white on black and black on white targets, and now all of a sudden a shadow comes across. And the vision system, which uses cameras, could not tell where those dots were, and they couldn't calculate the solution. Now, having flown in space 2 times prior to this, I was very worried about that. And so I spent an inordinate amount of time in our simulators, in our virtual reality labs, with our lighting experts, trying to model the lighting of what it might look like when it was within those very tight tolerance bounds. The other thing that happened that was never discussed, never planned for, is there was a malfunction in the Russian segment basically on the day of launch. And again, it was launched 2 weeks prior to us. And this is a communications antenna here. And that antenna was rolled up in a metal spool. And it was supposed to deploy almost like if you took an aluminum blind and rolled it up. And as it deployed, it self-closed, and then it became a rigid structure. But neither one, there was one on this side, one on the other side, neither one deployed. And so literally they told us, go out and bang on it. Now, usually you don't get guidance like that for spacecraft because usually they're very leery about you touching spacecraft and especially banging on it, but they thought it just needed a nudge. So the spacewalking crew members and I sat down and we developed an arm position where they could get in position. And then we fashioned this tool ourselves by taping things together in the shuttle and then taking it outside. And literally they were tapping on it. And what was not funny, but it was funny after the fact, is that Jim tapped on it a couple of times and nothing happened. And he tapped on it a couple of times and nothing happened. And so he started to turn around because the shuttle is back here. He's kind of looking back at the shuttle now. He started to turn around, and it was at that point it deployed and it shot right past him because it was in the middle of this thing was a spool that it was actually ejected out into space. And, all of a sudden we said, whoa, watch it. So he missed the entire deployment. And here's the antenna fully deployed. As you can see, we use and extensively use robotics. We use them to assemble the space station. We use them to service the Hubble Space Telescope on the shuttle. We use them to deploy satellites on the shuttle. And so there's a whole suite of robotic systems on the International Space Station as well. And 2 of the primary systems, it has a big remote manipulator system, just like the shuttle did. And primarily it's teleoperated. So teleoperated means you're not right next to this. You're inside at a control station. And we have 2 of them. This is in the US lab. This is in the cupola. Now the cupola is an amazing place. It's basically a window to the world. There's only one other window in the US segment. But this was specifically designed for robotic operations and during EVA operations when the person inside is giving the people outside instructions. And so it has windows all the way around it. And engineers think a perfect spacecraft has 0 windows because you worry about the structural integrity of the window, and there's micrometeorite and orbital debris that could hit the windows. And I was actually on a flight where we had a MMOD hit on a window. Luckily, it didn't damage all 3 panes. But from an astronaut's perspective, the more windows, the better. Because I often get asked, what do you like to do in space when you're not working? And it's look back at the Earth. I mean, what a fantastic view, what a unique view for the first time to see this universal perspective of the world. And our Earth is incredibly beautiful from space. And to see orbital sunrises and sunsets that, again, take place very quickly. And it's right at sunset, right as the sun starts to set, that the atmospheric band gets illuminated, and you can see striations of pink, green, blue, yellow. It's one of the most beautiful sights in the entire world. But what it also does is remind you of how fragile our Earth is, because it's that thin atmospheric band that's protecting us here on Earth. You saw just a few of the spacewalks, but over time, to completely assemble, starting with R3 here in 1998, we have done to date, and this is current, 182 spacewalks in US spacesuits and 55 spacewalks in Russian spacesuits. Now, when we do spacewalks in US spacesuits, we go out the US airlock. And when we use our Russian suits, we go out the Russian airlock. Primarily when we do US spacewalks, it's on all but the Russian segments. So the Japanese segments, the European modules, the US modules, the Canadian robotic systems, and primarily when we do spacewalks in Russian suits, they're on the Russian elements. I'm actually teaching a course this semester for both undergraduates and graduate students that talk about aerospace human factors engineering. How do you design aircraft and spacecraft so that you can operate, but as importantly, live in space? Remember, we wake up, we're at work. And when we go to bed on a mission, we're still at work. And so you need to design spacecraft not just for robotic operations and rendezvous operations and payload deployment or experiments, but you need to design them so that people can live in space. So of course, in the shuttle days, we had kind of basic sleeping bags. All of our shuttle missions were roughly a week to 2 weeks in duration. All of mine were roughly 2 weeks in duration. The longest time we ever flew the space shuttle was 17 days. And that's because we had a limit on our electricity. We didn't have solar arrays on the space shuttle. For electricity, we use cryogenically stored hydrogen and oxygen. So that's taking hydrogen and oxygen, supercooling them to a liquid state. You keep them in a tank, and then when they combine and make electricity, they also, as a byproduct, make water. But that's a consumable. Once it's gone, no more electricity. And so the longest we could ever fly was roughly about 17 days. Now, for 17 days, just if I was being deployed in the military, I can sleep in a sleeping bag. I don't even need a tent, right? You don't need a lot. But now for the space station, when people are flying average duration 6 months, 2 people have flown almost a year, 1 male, 1 female. Now at those extended durations, you need your own sleeping quarters, right? You don't want to climb in a sleeping bag and hang on the wall every night. You want to go to your room. You want to go to your room and get away from your roommates, perhaps, maybe just for a little while, and certainly during the night, and have a little bit of privacy. So this is just a glimpse. It's not big. And remember, it's not big for a reason, because in microgravity, not on planetary surfaces, where there is some element of gravity, right? 1/6 gravity on the moon, 1/3 gravity on Mars. But in a microgravity environment, every inch of that space is livable because I can sleep on the ceiling or I can eat upside down. And we'll talk more later about why we need to exercise in space, but you can see we have a treadmill. We have something called the Advanced Resistive Exercise Device. We just call that ARED. And then we have a cycloergometer. Now this bicycle is pretty unique because you see one big thing missing. It doesn't have a seat. You don't need a seat in space, right? You're just floating. I actually helped design these pedals, and I was doing triathlons at the time. And of course, you don't want your foot to slip off the pedal or float off. So we just use the same kind of clip-in bicycle pedals that you would use during a bicycle race or during a triathlon. And so I just want to play this other video very briefly so that you can see when you're designing equipment. So this is this advanced resistive exercise device. And you can see that you can just flip around, and now I can do squats. And so you could take one piece of equipment, and because you have the flexibility, even the bicycle, I could flip upside down and row with my arms and use it as an arm ergometer instead of a bicycle ergometer. This is the same US segment that I showed you a few minutes ago. And you might say, wow, look at all that stuff, right? And so everything we need for our space missions, and let's say we need a tool, something breaks and you need to go out to your toolbox. Well, it's got to stay somewhere and it's got to be inside. You don't want to have to do a spacewalk to go get your tools. And so you bungee it all down, but it takes up a considerable amount of volume. And when we're installing new equipment, you got to keep in mind that while it may be fairly voluminous, basically it kind of weighs nothing in microgravity. So if I want to take this huge piece of equipment, I can just guide it with my fingertip. I can just start guiding it with my fingertip. One of the things about tools is we have 3 huge refrigerator-sized bags of tools on the space station today. And you can see they take up a lot of room inside. And so one of the things that I've seen NASA get really, really excited about is advanced manufacturing in space. This is a printer already on the International Space Station. And you can see that just like if I were eating, if it has enough viscosity, it will stick. And so we have already 3D printed some tools on orbit, and you can see the 3D printer operating here. What a fantastic innovation, because each one of those tools weighs something, and the kind of standard value for what does it take to launch a tool in space is about $10,000 per pound, plus the volume that it takes out. So if we can manufacture tools that maybe we didn't think we might need on orbit, how fantastic would that be? If we can manufacture some of our equipment, you know, out in space or at our lunar habitat, or when we go to Mars, we're going to be pretty constrained on all the things we take to Mars. And that mission is going to be, you know, probably about 2 years in duration. A lot of things you got to take along. So there's thoughts about, could we 3D print food? Could we 3D print clothing? Could we 3D print even the volumes that we might live in? As I mentioned, as we look beyond low Earth orbit, and that's the path that NASA's on right now. We're going to get beyond low Earth orbit with just a couple hundred miles up in space above the Earth. We're going to go back to the moon and on to Mars. And I often get asked, why go back to the moon? We've already done that. And it's primarily one reason. There are health hazards of spaceflight that are numerous. And I'm just going to put up these lists, right? There are microgravity and physiological changes that happen, space adaptation sickness, fluid shifts, cardiovascular deconditioning, muscle atrophy, bone loss, because you're not loading the skeleton in a gravity environment, hence why we exercise roughly at least an hour a day, sometimes up to 2 hours a day. Isolation and confinement. I can't tell you how many times my phone rang after the start of COVID saying, hey, you astronauts are pretty used to this isolation and confinement. Do you have any guidance for people? And, you know, you have to be very cognizant of, there can be behavioral impacts of being on these very long duration missions, being very isolated, sleep disorders, because of the radiation effects, right? Increase in cancer risk. So astronauts are considered radiation workers. We have to wear dosimeters. They track every X-ray we get, and we have limitations on how much radiation we can be exposed to in our lifetime. It also, especially when we go out and do an extravehicular activity, or we do lunar exploration or exploration on Mars, right? We're in pressurized suits, so we have to deal with decompression sickness, extreme thermal environments, -200, +200, micrometeorite orbital debris damage, and then partial gravity environments, you know, 1/6 G on the moon, 1/3 G on Mars. Now, what we don't know, these health effects, what happens to the human body in 16G? Is that closer to what happens in 0G, or is it closer to what happens to us here on Earth? What about 1/3 G? So the best thing to do is to study that on the moon that's just a few days away before we send people on a mission that could be 2 years in duration. So the next bold mission for NASA, back to the moon and on to Mars, right? Establish a planetary habitat on the surface, establish a gateway, a space station operating in cislunar orbit. And so you could be on the space station in lunar orbit, take a trip down to the moon, do your exploration of the moon, go back to that orbiting platform. And then, as you know, currently today, we have the rover Perseverance. This is the Ingenuity helicopter. But our vision is for human presence on Mars. So we really need to understand and fully appreciate all of the things that happen to human physiology in these exceptionally long duration missions. As I said, we've only had 2 crew members fly for 1 year. And now we're talking about missions that are maybe up to 2 years in duration. I'm going to show you one more movie. Yes. Turn it down.
We are the explorers. We have a need to find what is out there. It is a drive inside each and every one of us. The drive to wonder, to push the boundaries, and to explore. We expanded across our lands, settling new frontiers. We took to the oceans and learned that we could cross treacherous expanses in the pursuit of discovery. And then we took to the skies and flew. But that wasn't enough. We left the planet and redefined what was possible. We flew in space. We walked in space. What once was a melodramatic Then, a new generation of spaceships captured hearts and minds for 3 decades and helped build a castle in the sky that is our lasting home in space.
Okay, I'm actually on my last slide. So my question to you is, after seeing kind of a little sense of what I've done in my career, what bold steps will you take? And what dreams will you realize? And hopefully your goal will ultimately result in making the world a better place for all mankind. The benefit in space exploration is what we learn. One of the benefits is what we learn about human physiology, and that has direct application for a lot of our aging population. And so I'd implore you that throughout your career, and not to chase economic goals or not to chase big titles, but to truly chase your dreams and to be very passionate. You know, the best thing in the world is to wake up in the morning and you just can't wait to get to work. And getting a paycheck for what you're doing is almost like a bonus. And have the sense that what I'm doing is making a difference. So whether that's being an architect, whether that's being a doctor, whether that's being an engineer, whether that's maybe being an astronaut, you know, what will you do to make the world a better place for all mankind? So with that, hopefully looking at some of the slides and the video, you might have some questions as we have gone on. So we can go ahead and open it up for question and answer now.
Thank you so much for that wonderful presentation and talk, Dr. Currie-Gregg. We've got some questions for you from the chat. The first one is from Lila and asks, how does the study of math and science relate to astronomy? And also, what schools best prepare students for a career in astronomy?
That's a really great question. Sometimes I come across students and they raise their hand and they say, what's the easiest degree I can get and become an astronaut? And I tell them, well, that question's kind of got some fundamental flaws in it, right? You can see what we do is highly technical. Same thing with physics and astronomy. It's a highly technical field. And so you may get to a point in your education, and it may come sooner than you think, and it's probably going to come even before your college days, where you get to choose, do I continue to take math and science? You know, maybe you think they're difficult classes, but you need to challenge yourself. It's extremely important. You just look at the technology that we have today. What I have on my iPhone is more computing capability than we had in the space shuttle. You look at autonomous vehicles, you look at some of the robotic systems that are used in the medical arena. All of that requires math, science, engineering, and technical skills. So no matter what your goals are, math, physics, engineering, the sciences, it's very important to have those fundamentals at an early age, as early as possible, so that when and if you do enter college, if that is your goal, you are very prepared. With respect to what institutions, here's my personal guidance. I had to go to school on scholarships. My family could not afford to send me to school. And so I was I had been a product of public education, a first generation student. At a university, it's what you make of the experience, no matter where you go. I know of astronauts who started out in junior colleges, but they worked very hard in junior colleges, got the foundational experiences they needed in the STEM fields, and then entered a university and ultimately majored in one of the STEM sciences. And so it's not so much there's preferable schools, it's what you do with that experience. So that's a great question.
Awesome, thanks so much. Our next question is from Steplight and asks, how far into space have you traveled?
On the space shuttle and the International Space Station, they both travel in what we call low Earth orbit. So literally, it's just a few hundred miles above the Earth. And so when you consider how far away the moon is, you're just a couple hundred miles, you know, closer to it than you are here on Earth. But the really unique thing is, of course, you're up above the atmosphere. So one of the things is, oh my gosh, you see an incredible number of stars in the night sky during the, you know, of course, you have a darkness pass every 45 minutes in space. And so the moon does look a little bit closer because you're not looking through the obscurations of the atmosphere. So my missions range from 160 miles up to the Hubble Space Telescope is 350 miles up, and the International Space Station 215 miles from Earth.
That's really crazy to think about. I forget how far it is to Dallas from College Station, but that's almost a drive there. Our next question is from Athena, and it is, what is the most unexpectedly fun thing you did in zero gravity?
Most unexpectedly fun thing. A lot of fun things because we're like big kids, right? One of the things that astronauts like to do is have contests of how many somersaults can you do, because once you get started, there's really nothing to stop you, and you're not going to get sick because your vestibular system isn't being accelerated. So you can theoretically, do quite a large number of somersaults. The other thing we like to do is act like we're ice skating, and we can start rotating, and then as we close our arms, we speed up, and then we can slow ourselves down. So that's always fun. And then all astronauts, at least initially, have to play with their food, because it's the only place in space you can say, literally, toss me a jelly bean, and you can kind of fling it across, and it'll float across the room, and then you can just open your mouth and eat it. So I would say that there's quite a bit of video of astronauts playing with their food on orbit.
That's really funny and actually quite ironic you mentioned the food. Our next question is from Mathematics Kid. What do you eat in space?
So on the space shuttle, it was a little bit different. As I mentioned, we use cryogenically stored hydrogen and oxygen. As a byproduct from that, we made H2O. And some of that water we used to cool the shuttle systems, but some was used for potable water. And so it was advantageous to fly dehydrated foods on space shuttle because you had this infinite water source as a byproduct of making electricity. And in fact, we made so much water that every few days we had to dump it overboard, which is a pretty fantastic thing to see, because as it was ejected out into space, it immediately sublimated into ice, and it looked like you were flying through a snowstorm in space. So we used primarily dehydrated foods. A little bit later on, we use some meals ready to eat, just the same thing as the US military uses, thermal stabilized food. And that is the primary source of food today on the space station. Now, you got to keep in mind that there are astronauts literally from all over the world flying on the space station, right? There's Russian cosmonauts and Japanese astronauts and US astronauts and European astronauts, Canadian. And everybody's got their own cultural taste in terms of food. So it's very important to consider, again, living in space. So if you're a Japanese astronaut and you're used to a certain way of eating, you don't want to be told you can't have enough food. You need to eat Russian food for a year. And they actually tried that early on. And of course, astronauts were losing a lot of weight. When you lose a lot of weight, you can have, physiological issues that result from that. So it's very important. All of us think food's pretty important, right? If we really want to have a morale boost on the space station, we might send up, along with some frozen samples that we want them to experiment on, we might sneak in some ice cream. And boy, is that a big hit, right? We don't normally have ice cream. And for those of you that have sampled the astronaut ice cream, that dehydrated chunk of sugar, I hate to break it to you, but we never flew that. Or if we flew it once. Could not even convince my own father of that. He thought he had tasted astronaut ice cream. But, whether it's fresh fruit or whether it's, marshmallow puffs or, everybody's got their own thing. In space, I like Teddy Grahams because I like to float little teddy bears around. And when I throw it to other people, whatever it is, that can actually be, kind of a real morale boost. And you need to actually think about those things and plan for them.
Very interesting. Our next question is from Ethan. How was the flight up to space in the shuttle?
It is a fascinating experience. The first thing is it's really short. Believe it or not, you go from sitting in the launch pad, Kennedy Space Center, to when the main engine's cut off and you're up in space, 8.5 minutes. So you think, even here in College Station, not a lot of traffic. Some traffic with the students around, but not a lot of traffic. But I think about, in Houston, where I lived for 30 years, how far can I go in 8.5 minutes? On a good day, maybe a few blocks. But in shuttle, I go from sitting on the launch pad and now I'm several hundred miles up in space in a microgravity environment. So getting through the densest part of the atmosphere, we used 3 space shuttle main engines that were fueled by gas in that big orange external tank that you see. Again, we use liquid oxygen and liquid hydrogen to fuel those. They each produced about 375,000 pounds of horsepower. And then the 2 big solid rocket boosters on the side had about 3.1 million pounds of thrust apiece. And that's to get us out of the densest part of the atmosphere. And then once we're out of the densest part of the atmosphere, those solid rocket boosters would actually come off and they would actually parachute back down. They would retrieved and then refurbished and reused on subsequent shuttle missions. They'd actually fall back into the ocean. And so in first stage on those solid rocket boosters, it is shake, rattle, and roll. I mean, you shake, rattle, and roll like you've never experienced. And in fact, in our simulators, we couldn't simulate that level of vibration because it kept damaging our simulators. And so there's no doubt when the 3 engines light and the solid rocket boosters light, and you got 7 million pounds of thrust. The shuttle weighs at that point, fully fueled, about 4 million pounds of thrust. There is no doubt in your mind that you are in a real spaceship being rocketed off the planet. And you just know you're leaving town very quickly. And then once the solid rocket boosters come off, you continue on the 3 space shuttle main engines for about the next 6 minutes. And near the end of ascent, they actually have to throttle back so that our acceleration is not more than 3 times gravity. And that gravity vector, because I'm laying on my back, is right through my chest. So at 3G, it feels like somebody 3 times my weight sitting on my chest. So I described it as noticeable to take a breath. So again, you know you're in a rocket ship, you know you're going very quickly, noticeable to take a breath. If I tried to raise my arm weighed 3 times its normal weight. So, you know, raising my arm was difficult. But you go from that to main engine cutoff and boom, you release your seat belt and shoulder harness, and then you float up. And according to people who flew with me, I got a big smile on my face and it stayed there till the second we landed. Just an incredible experience.
Wow, that's really interesting. So then our last question is from Lucy Yust and asks, have you ever seen the Aurora Borealis from above? What did it look like?
Oh my gosh, what an excellent question. I have, and indescribable. Unfortunately, the best view I had of it was on the Hubble Space Telescope mission. And because we were flying as high as the shuttle ever flew, 350 miles, the radiation exposure is higher up there. And so we couldn't fly any high-speed film because the film would have fogged. And this is back in the day when we were flying film cameras. And we had this incredible pass where we came across, and it just looked like these blue-green columns of light. You can see some of the images. They have been able to capture some of the images from the space station. And in person, it's just breathtaking. It's just like this image I'm showing here on the screen of, you know, you can look down at the Earth at night and see major cities lit up. One of the most interesting passes we had was on the Space Station Assembly mission, right up the East Coast of the United States, right by Atlanta and New York, and all the way up to Boston. And when we got to Boston, if we got in the corner of the window, we could look back all the way to the Florida Keys and see the whole East Coast of the United States lit up. And it's those kinds of views why they talk about this thing called the overview effect with astronauts. And I can tell you that once you've experienced that kind of universal perspective of the world, it changes you forever.
Yeah, that does really seem to be life-changing. I wish a lot of us would be able to see something like that. Maybe not so far into the future we'll be able to. Thank you so much for everything. That was wonderful.
Well, thanks so much. And for any of the kids, the teachers, you know it's a challenging time. Definitely, I've been in confinement in space and now here on Earth, but it's all worth it. So try your hardest. Again, try to take it one step at a time to achieve your goals, but always challenge yourself to do better and to achieve the ultimate of helping everybody on this planet that we all live on. So thank you very much.
Dr. Currie-Gregg, I also would like to thank you for this amazing glimpse that you gave us into how it is to be an astronaut, and also what future holds for human exploration of space, and what kind of future NASA programs await us. I would also like to thank you for everything you have done and doing for the university and for this nation, as a pilot, as an astronaut, as an engineer, as a scientist. And also, you've shown such a support to our physics and engineering festival through all these years, and I would like to thank you for that very much. Thank you, Dr. Nancy Currie-Gregg.
Thank you, and thank you for the opportunity today.
Have you ever tried to power a light bulb with a bike? As weird as it sounds, it is possible. As the crank spins the magnets about the copper wires, changing magnetic flux will generate a current, which in turn will illuminate these light bulbs. In real power generating plants, it is wind, hot steam, and wind which rotate, and water which rotate the magnets. This electromagnetic bike generator will show you just how easy it is for us to generate electricity using a principle known as electromagnetic induction. In this demonstration, we're going to generate electricity by rotating this crank, allowing these magnets to spin about the copper wires behind them and generate currents. As you can see, we have 3 light bulbs here. They're all different. Whether or not these light bulbs will light up is a question of power. So each light bulb will require a different energy input. So as you can see, when I come over here to turn these on, we're going to start with a 20-watt light bulb. The question is, do I have the strength required to turn this light bulb on? Well, that wasn't too hard. What about this fluorescent bulb in the middle? It's only 9 watts, so it should be a lot easier. And it was. Now, what about this 150-watt incandescent bulb? That's way more wattage than the other 2. Well, it was a little harder. But now the final question is, do I have the strength to light all 3 at the same time? Let's find out. What's going on? It's not working. I did it. Well, that was the electromagnetic bike generator. I hope you enjoy the rest of the festival.
Howdy! All of you are really bright. And I don't just mean that you did well in school or that your mother calls you son. I mean that you're glowing. And that's because you're made of atoms and molecules which have temperature, and because they have temperature, they're moving. And the atoms and molecules that make up your body or everything else are made of electrons and protons, so that random motion means they emit electromagnetic waves. Now, when things are really hot, they emit light that you can see. You've heard of things that are glowing red hot. But even at room temperature, our bodies and everything around us are also glowing, but they emit infrared light that your eyes can't see. And I have an infrared camera that can pick up those wavelengths. So what do you see? Okay? You see my glasses are dark. They're at a lower temperature than my skin. You can see my really hot mouth. See? Or my cool beard. Okay, that was a joke. You could laugh. Oh, you're a tough audience. I mean, this entire thing, the whole physics festival, was just so I could do that joke. Okay, I'm kidding. So let's think about some things, what we can see. Look, just like your eyes have different rods and cones that are sensitive to different colors, so that gives you color vision. The infrared camera has more than one infrared sensor, so it can map different temperatures to different colors. And with the software that you see is mapping hotter temperatures to red and white and lower temperatures to blue. And with the right calibration, you can even measure the temperature. And that's what this spot in the middle is showing. It's showing right there on my neck is 93 degrees Fahrenheit. Look at some other things. Now the camera automatically adjusts when you get different things at different colors. So let's pour some hot coffee into this mug. And you can see what happens. See how the mug starts to glow? It's now gotten quite warm, and the camera is mapping its color to white. I can take ice water, which is really at a low temperature, so the camera is showing it as black. If I put some in my mouth, it'll turn my mouth black. See? Now, some things are transparent, which means light goes through them. Glass, you know that light goes through glass. But there are some materials that will stop the light that your eyes can see, but will still allow infrared light to go through. Here is a latex balloon. I'll hold it in front of my face, and now you can see the visible light is stopped, but the infrared camera sees right through it and can see my face perfectly well. You don't want to put a trash bag over your head, but if you wanted to hide behind one, oh, it's pretty effective to visible light, but the infrared camera sees right through it. Some people want to know what happens when you put on a mask because of COVID. Think about this. What happens when I inhale and exhale? Let's do it. Inhale. And now exhale. Did you see what the mask does? Now, you can even leave secret messages. Let's show what happens if I put my hand on the screen. Now I take it away, and you can see the message left behind. What you see is that I warmed that screen just a little bit, and it's still glowing. I hope you've learned something today. Everything is glowing. It's glowing because it has temperature. If things are really hot, they emit visible light. Around room temperature, it's infrared. And even things like supercooled things like liquid helium or the vacuum of space, they emit microwaves. But that's another story. So for now, stay safe and goodbye.
Hey everybody, I'm willing to bet that Max and I can blow your minds with just a couple of weights, a rotating wheel, or rotating chair, and a bicycle wheel. So I'm going to start off with these weights, and just going to get spinning on this chair. It's pretty mind-blowing, right? Now, it is pretty boring, but watch what happens when I bring my arms in.
Matthew starts spinning a lot faster. Matthew's probably getting kind of dizzy, so if he wants to slow back down, he can stick his arms back out and move the weights away from his body. In physics, we call the amount of spinning something has angular momentum. And this angular momentum, or the amount of spinning, is a conserved quantity, meaning it stays the same over time. And since it's a conserved quantity, and it depends on two things, how far the weights are away from Matthew's body and how fast he's spinning, when he moves the weights away from his body, he has to slow down to conserve angular momentum, and vice versa, when he moves them towards his body, he has to speed up to conserve angular momentum.
Oh, I promise you that feels a lot faster than it looks. But if you want to feel it for yourself at home, all you need is a rotating chair and a couple of heavy books, and you can feel it for yourself.
Not only does the amount of angular momentum like to stay conserved, but so does the direction of angular momentum. And to show that, I can get this bicycle wheel spinning. And you can see, as I try to change the direction of angular momentum, I can really feel the bicycle wheel fighting me.
Well, so at home, how do they know that it's actually fighting you if they can't feel it for themselves?
Well, let me sit on the stool, and I can show you. And as I tilt the wheel, I start spinning.
So as you're changing the direction of angular momentum, you have to start spinning to compensate for that change.
Exactly.
And so what if you bring the wheel back upright?
I will stop spinning.
So then if you tilt the wheel the other way?
I can spin in any direction I want. Actually, this is how the International Space Station can turn in any direction it wants.
Cool. But what if they're still not convinced?
Well, I can show you if we get this spinning one last time and see if you can guess what happens when I let this wheel go.
So the angular momentum of the wheel wants to stay the same, but a torque due to gravity doesn't make the wheel fall down, but it makes it rotate around the direction of gravity.
Exactly.
I'd say that's pretty mind-blowing.
Enjoy the physics festival.
Okay. Hello everyone. So today I want to play with one of the coolest things that we have here at the Physics Festival, and that is liquid nitrogen. Liquid nitrogen chills at a cool temperature of a negative 220 degrees Fahrenheit, around 400 degrees cooler than the temperature of your skin. It is used in a lot of different fields of studies in order to cool down objects to sub-zero temperatures. But for that reason, it is very dangerous to play with. So in order for me to continue onwards, I will need to wear some safety goggles just in case. Okay, so what makes it so dangerous? Well, consider an ordinary object like this racquetball. At room temperature, it is malleable, flexible, and very bouncy. But once you cool down an object to sub-zero temperatures, at one point it reaches what is called the glass transition temperature. And what happens is that they become more dense and brittle, behaving more like glass. For example, right here I have a racquetball that was cooled down to sub-zero temperatures, and let's see what happens. Oh, well, that shattered. May not have been in frame, but you guys can still hear that. Okay, so people tend to ask me, if it's so dangerous, what would happen if you put your fingers in there? Well, I don't want to do that. So over here I have this hot dog that would take place for my fingers. It is very malleable, flexible. I can also twist it and bend it until it breaks, just like I can do with my fingers. But since I'm not doing that, I'm gonna actually use a different hot dog that has submerged in liquid nitrogen as a replacement. let's see what happens here again. And, wow. Okay, so there you go. If I actually used my fingers on this, I would have 10 tries, but I don't want to go in that route. But I don't want to be all doom and gloom about physics and liquid nitrogen and how dangerous it is. So I want to show you guys a little bit of romance in physics. Right here I have a yellow rose. So pretty, and oh, it smells so good as well, but I'm too cool for love. So if you give it some time in the liquid nitrogen, it will be submerged to around about negative 300 degrees Fahrenheit, around there. And let's see what happens. I take it out, and it breaks just like glass. Well, that was fun, but I was caught in the heat of the moment. So next up is Dr. George Welch, and he'll be going over what heat actually is and how it pertains to us in the universe.
Hey everybody. So believe it or not, here you're going to see a train levitating in midair. And the way we're going to do that is by using these ordinary looking ceramic pieces. But these are far from ordinary. If we cool these down with liquid nitrogen, then the resistance of these pieces the electrical resistance of these pieces will drop to 0. So when you turn on the lights or power up your electronics at home, you actually lose some energy due to the electrical resistance in the wires. So when I cool down the ceramic piece and the resistance drops to 0, it acts as a perfect conductor with no energy loss. That's why we call these special materials superconductors. So we have some that are already cooled. What is this? And that we're going to put over our special magnetic track. So this is So this is just an arrangement, a specific arrangement of some smaller magnets that was built by some students at Texas A&M. And so if we put a superconductor over the magnetic track, we see that it levitates. And that's because the magnetic fields are partially penetrating the superconductor in the form of tiny vortices and holds it above the track and keeps it on its path. So you might notice that it's starting to slow down a little bit. That is due to air resistance, not electrical resistance, because superconductors don't have electrical resistance. Eventually, as these superconductors warm up to room temperature, they're going to lose its superconductivity and they'll fall. So if we want to keep it levitating for longer, we need to keep it cooler for longer. So we have a special made container with a set of superconductors filled with liquid nitrogen to keep it cold for longer. And I promised you a levitating train. And here we have a little train cover that was designed and 3D printed by some students, again, at Texas A&M. Now, yeah, and you can even see that you can put things in the way and it'll just float right over them. So it is truly levitating over the magnetic track. So maybe trains aren't that interesting to you. We have something maybe more exciting. We have the superconducting roller coaster. So here we have an uneven surface of, again, smaller magnets. And if we place the superconductor on the track, you see that it still levitates, and it also still keeps the same distance away from the track. And it just smoothly goes back and forth. Now this might be a little boring compared to some of the roller coasters that you've ridden, but we'll see if we can crank it up a notch. We can actually, by using the power of superconductivity, actually turn this roller coaster upside down. So we get one of our cold superconductors, and we see that it still levitates from the track. And so I don't know about you, but the excitement of riding a roller coaster that's levitating and upside down is far better than any roller coaster that I've ever ridden. So superconducting trains, superconducting roller coasters, this is just scratching the surface of what we can do with superconductivity. The one issue is that it's very expensive to keep these superconductors cool for long periods of time. So if you find a room temperature superconductor, then a Nobel Prize is guaranteed.
Howdy. So, we've played with a lot of liquid nitrogen today. Earlier you might have seen when we cooled racquetballs and flowers, they shattered when they were cooled with liquid nitrogen. Or you might have seen the train that floated over magnets when it was cooled with liquid nitrogen. And if you were watching even earlier this morning, you saw us do what was called a 5-barrel depth charge, where we filled some soda bottles with liquid nitrogen and sunk them into barrels of water, and they all exploded. In this demonstration, we're going to take a slightly closer look, and I'm going to explain what happened in that demonstration with a single barrel depth charge. So what we're going to do is put about 1/3 of this bottle's worth of liquid nitrogen in and sink it to the bottom of that barrel and see what happens. What we know about nitrogen is that when it's in its liquid form, it takes up about 700 times less volume than it does when it's in its gaseous form. So when this bottle is sealed and that liquid tries to expand into that 700 times volume, well, we'll see what happens. So, safety first. Got my liquid nitrogen. Thanks for watching. Stay tuned for the finale where we're going to do another 5-barrel depth charge.
Y'all been asking a wealth of questions, so let's get some of those answered. We'll first be joined by Dr. Dawson. Welcome back.
Hi, Billy, I hope I pronounced your name correctly. I asked a really awesome question about the superconducting train and whether or not there are actually real superconducting trains that are around it, in our world. And the answer is yes, actually. Maglev train technology, there's a particular type of it called electrodynamic suspension that uses real superconducting magnets to actually propel a train. Now, the problem, as was stated when the presenters went through the demo, is that it's hard to do superconducting trains because you have to keep these magnets really, really cold. So it's really expensive to constantly cool down your superconductor to keep that train levitating. But yes, it is possible. So if you are able to find a superconductor that works at room temperature, you can win a Nobel Prize, guaranteed.
Wow. Thank you. Our next expert will be Christian Cernal. Welcome.
How's it going?
It's going all right.
So somebody asked, they saw me flip the switches during the electromagnetic bike demonstration, and they asked, was it plugged in? The answer was no, it was definitely not plugged in. The switches determine where the current gets to travel. So by flipping a certain switch over another, I get to send current to a specific light bulb over another. So that's it. Otherwise, it was not plugged in. It's all just, magnetic flux that's generating the current.
There you have it. Our next expert is Dr. George Welch.
There was a question about the demo I did Eli Krasnov asked if the spot in on the television was interpreting the color as a temperature or directly sensing temperature. And it's more or less directly sensing temperature. But it's interesting because that camera works the way your eyes do. Your eyes have rods and cones. Different types of cones sense different colors, and your brain then interprets that. The infrared camera, it's sort of like a colorblind person. It has two color sensors. And by looking at the difference between the signals that it gets from each, it figures out what the temperature has to be, because every different temperature emits a different infrared spectrum. So actually, it's a lot of computer processing going on, as well as the sophisticated infrared sensors.
Wow. It's really crazy hearing that, to think about what your brain does so that you can see things. Our next expert is, once again, Dr. Dawson.
So Brenna Allen asked a question, what machine transfers motion or movement into electricity? And really, it's any moving magnet with a coil of wire. So really, as long as you have some method to move a magnet through a copper coil, you can induce a current and thus generate electricity. So it's really all about how do you get those magnets to move, or if you want, you can get the wire loop to move. It's all about motion of the magnet relative to the copper coil to generate that current. So you can have animals walking around constantly trying to move essentially a pulley, so that way you can turn something. You can generate this type of current in a number of different ways, just depending upon how inventive you are. But to generate electricity to power our modern world, we really need things that can really move, in a sense, magnets really quickly, so we can generate those currents. I'm joking a little bit, but you get the point.
Yes, of course. Thank you. Our next expert is Adrian Thompson.
Hey, thanks very much. So this is not a question, but this is just something that I get reminded of every time I study angular momentum or I teach about angular momentum. There's a really, really cool demo that exemplifies how angular momentum, like in the bike wheel, can affect motion. And there's this thing called a cubely that you can look up if you like. It's basically a little cube with a metal frame, and there are actuators with wheels on each side of the cube. And by controlling the rate at which those wheels spin, you can actually give the whole cube a kick in angular momentum. And in fact, by controlling the spinning of the wheels very precisely, you can actually get it to lift up and stand on its edge, balanced perfectly, just by precisely controlling the angular momentum. And again, that's because when you have these rotational forces, they exert a torque on the whole system. And this is what causes the whole thing to rotate. So it's just kind of a cool little demo that I think is always really cool to kind of get your mind wrapped around how these rotational forces cause these kind of complex motions.
Yeah, that is really cool. I wonder if we could incorporate some sort of actuators into the spinning chair demo.
That'd be
really neat.
Yeah.
All right. Well, thank you so much, Adrian. Next, we have Dr. George Welsh.
I saw a question further back from earlier on by Yuki Pant. And by the way, I love your handle. About why does the rose break so easily? And I thought that was very, very interesting. It's because all of the water in the rose gets turned into ice. And you can break ice. Imagine having an icicle that you take off the side of your house, and you can shatter that icicle. So anything that's organic, like the rose, has got a lot of water in it. And that liquid nitrogen froze that water into ice. So then the rose became basically just like ice, which would shatter.
Very neat. All right, and with that, let's move on out of the Q&A. So those demonstrations that we had earlier were wonderful, and we have more of those coming up soon. But first, remember, if you have any more physics questions, please post them in the chat. We've got a bunch of experts to answer them, and we would love to see them answered. In fact, here in the studio, as we've just been doing. And also, don't forget to click the big subscribe button. We may feature your name on the screen. And also, don't forget that we have a surprise bundle to give away with goodies like a t-shirt, glow-in-the-dark frisbee, skyhook, diffraction glasses, and more delivered to your door. Simply go to tx.ag/science giveaway. There's a link for that on the screen as well. Finally, be sure not to miss interacting with the scientists and more demos live at 2 p.m. Central. Zoom links for that will also be available at tx.ag/festival schedule. A link for that is in the description. Now let's get ready for our second speaker. This is another chance to take a quick break.
Dear guests of the festival, friends and colleagues, thank you for joining us for this next portion of the program, in which we are very pleased to welcome the keynote speaker of the 2021 Texas A&M Physics and Engineering Festival, Professor David Saltzberg. David is a professor of physics and astronomy at the University of California, Los Angeles. He's also chair of the department there. He's an experimentalist working in the field of particle physics that aims to understand the most fundamental laws of nature and the evolution of our universe from the Big Bang to modern days. David's accomplishments span over a broad range of particle and astroparticle physics research topics. He has received his bachelor's from Princeton, and then he did a PhD at the University of Chicago, working on the CDF experiment at the Tevatron. That's a place where our paths first overlapped. Then David worked on a chorus experiment at CERN, looking for evidence of neutrino oscillations, which we now know that they exist. Later on, David led the group at UCLA working on ANITA experiment in Antarctica, searching for ultra-high energy neutrino events. And nowadays, his primary focus on the CMS experiment at the Large Hadron Collider, where David and I have joined forces on several research projects. In addition to being an accomplished researcher, a wonderful colleague and a good friend, David is also a fun and engaging person to be around. And also, unlike many of us, when he gets out of his lab, instead of going home, he does science consulting for television shows, including the Big Bang Theory and Young Sheldon. And today, David will share us some of the experiences of that side of his life and how it feels to be a scientist in Hollywood. So welcome, David.
Okay, well, thank you very much, Alexei. And I really wish I could be in person at Texas A&M. I always like being there. And I thought I would tell you a little bit today about what I know about how Amy and Sheldon won their Nobel Prize. So, oops. Okay, so who am I? I thought I would tell you, Alexei told you a little bit. I thought I would tell you a little bit about who I am not. I am actually not a television writer, even though I joined my friends at the strike, which you can see there from about 15 years ago. But starting in 2006, I became the science consultant for the TV sitcom, The Big Bang Theory, which by now most people have heard of. And I never knew in 2006 that at this point we would have completed 12 seasons and 279 episodes. So rewinding the clock and going back to my first feedback, I was having dinner with my old professor, Professor Simon Swarty from University of Chicago, and he had told me he was watching a TV show. And he said, I want to tell you something. I was watching a TV show, and then here was a scene from the first season.
Hey, do you want to see something cool? I can make this olive go into this glass without touching it. How? Physics.
Wow, centrifugal.
So you hear they said centrifugal force, which those of us that know physics know that's not what's going on. It's centripetal. So and he said he heard that, and he said, yet another case that we physicists are used to of centrifugal force being wrong. But in fact, a genesis of the scene was I saw that word in the script, and I told my friend Bill Prady, who wrote it, about it. And let's just watch the rest of that scene.
Wow, centrifugal force.
Actually, it's centripetal force, which is an inward force generated by the glass acting on the olive. Excuse me. Now, if you were riding on the olive, you'd be in a non-inertial reference frame and would...
And so we got all of that science in there, and my friend Professor Swarty said the character launched into a physics lecture about centrifugal versus centripetal force that was completely correct, and I fell off my chair. And then he said he had to watch the rest of it, and he saw from the credits it was me. So that was my first feedback back at a time that not that many people were watching the show, and I was really proud that my previous professor approved of what we were doing. And so the thing I eventually learned is you can ask yourself, what is this scene about? Now, I think I would have, in the old days, said, well, this scene was about the difference between centripetal and centrifugal force. But over the years, I've eventually learned from the writers, this scene is not about that. This scene is about a boy trying to impress a girl on a date. And that's a lot of what to need to understand the science behind the Big Bang Theory. It's human stories, real stories about real people, but the science is there to add the flavor and the reality. So in the beginning, I had no trouble with these characters and understanding what they do. Raj is an astrophysicist. I do some of that. I can help with that. Howard is an engineer. You know, we do a lot of engineering as experimental physicists. Leonard is an experimental particle physicist-ish. You know, we've given him a few things to do, and that's what I do. And Sheldon is a theoretical particle physicist, which I can fake a little bit. And so we were doing okay. I want to note a little shout out here to the hidden hero of the show you don't see. There's actually something called props, which is anything an actor touches or something that's featured like this robot in this episode. So Scott London was the props master, and an incredible amount of work went into things that you see on the show. It's almost like another character in the show. So if you're watching it, pay attention to the props. A lot of work goes into that. So then trouble for me ensues because they started bringing in life sciences. Beverly, who's the mother of Leonard, is a neuroscientist, and I can't really fake that too much, and a psychiatrist. Bernadette is a molecular biologist, became the wife of Howard, and Amy, who became Sheldon's girlfriend and then wife and co-author of papers, is a neuroscientist. Now, what was really cool was Amy is played by Mayim Bialik, who has an undergrad and PhD degree from UCLA in neuroscience. So I never had to worry about her pronouncing anything. I tried not to rely on her to fix things. I would feel bad if she had to fix something in the script. So we worked pretty hard. These are not my field, but I tried to learn as much about it. And I have friends in these fields that I often called on for a little help. So some people have asked me a question like, oh, are these characters on this show stereotypes? And you just need to do a little bit of math to figure out if that's true or not. If you watch one episode and make a judgment, well, an episode's about 22 minutes. There's 7 characters. It's about 3 minutes each dedicated to each character. So if you watch, say, the pilot, or if you only watch one episode, you're not going to spend a lot of time on each character. It's not going to be very deep. And you might think these are stereotypes. But remember, the total series was essentially 140 hours. So no one is going to watch 140 hours of stereotypes. And I have a really good example, something that surprised me actually back in the early of the first season, but gave me a really good idea of how the writers write. And so, for example, those of us that know about people that like science and so forth might think these are guys that know a little bit less about sports and football. And so let's just see what actually happens in a scene where that comes up.
You're watching football? There's no fooling you. Now, what is this sack statistic they put up there?
All I know about sacks is my mother shops there.
Sacks.
It's football nomenclature for when a quarterback is tackled behind the line of scrimmage.
Huh. Scrimmage.
The line of scrimmage is the imaginary transverse line separating the offense from the defense.
Oh.
Sheldon knows football?
Apparently.
I mean, Quidditch, sure, but football?
Okay. So in the end, you realize this is actually makes sense. Of course Sheldon knows football. He's from Texas and he loves rules. So of course this puts in perfectly. And I asked the writers about this and they explained to me, they put the characters into a situation and then they think about how would that specific individual react? And that's how these become more and more real people. a lot of the writers are not always thinking about an endpoint. They're thinking about a situation, putting a character that they know and love into that situation, and ask how would they react. And I think that's what makes the show feel really real, and what makes these characters transcend what would be a simple stereotype. So what did I do in this? It's hard to believe it's over. So a lot of my connection was with the writers and the cast. We had several visits to UCLA where they saw my labs. They met graduate students, undergraduates, postdocs, and so forth. At one point, we had an experiment that had some black drapes around it to keep light out, and the actors were able to say, "Well, that's just like the theater." And so, for example, I was proud to show them something really special in our department, which is the remote Keck telescope observing room. It's where students go and take data from telescopes in Hawaii, but with all the apparatus controlled from our department. But the writers, they saw it for what it really was. It was just a conference room with a computer in it, ultimately. And they really like that. And then if you think about back to the show, there are scenes that take place in a telescope room with Raj very often. And they like that. And it also was a way to have to put the characters on a plane to have them do science. In general, I had lots of emails, lots of texts, lots of phone calls, but it was important that I went to the tapings. As you can hear the laughter, it's taped in front of a live studio audience. I often brought physicist guests. Sometimes they were undergraduate students, sometimes they were Nobel laureates, and they got to meet them, share their stories. But it was also really important for me to be in contact with the writers and so forth at a regular basis, because if you only connect to someone by email, you can start to lose contact. It was really great in person because a writer might be thinking about an idea of a story to pitch, but wasn't really ready to put it in an email, but we could talk about it over coffee, for example, or over a little bit of dinner while the taping is happening. And so, as I said, you heard this laughter. We were accused of having a laugh machine. This is in front of a live studio audience. Part of the reason you only ever see 3 walls in their apartment, we don't know what the other wall looks like, because this is what's in the direction of the other wall. And this kind of comedy, it's called a multi-camera comedy, where there's 4 cameras and an audience, is a lot like going to the theater. So when you're home watching and you hear the laughter and you see the actors walking around, it's an experience very close to going to the theater. And I think that's why it works really well. Something I learned from this with this audience is I'm used to particle physics experiments. We have theory that comes out, maybe a theorist spends a week on a theory, then we work for 40 years and we find out yes or no, that theorist was correct or not. And what's amazing is it turns out the comedy is empirical. You can think your joke is really funny that you wrote, but the scenes are performed in front of a live audience in order, so they're following the story, and the audience either laughs or not. You can't really argue if they're not laughing. It's a little hard to argue that your line was so funny because they are not laughing. And it was amazing because the writers would then go into a huddle. They would immediately know what went wrong. Even after 12 years, I wouldn't quite know. And it was sort of equivalent to be, if I were in my lab with a student and we heard just the right sound, we would know something is broken and we wouldn't even have to talk about it. We would know how to go in and fix it. And the same thing was happening here with the writers. They had, decades of experience, each of them. And so they'd immediately know the laugh wasn't there, or the laugh was the wrong kind of laugh, or they laughed in the wrong spot, and they'd quickly huddle, and somebody would whisper the new line into the actor's ear, and off we would go. They would retake the scene. So it was very much like experimental physics. Some of the other things I do, so I talked to writers and such about the stories very early on, but then I would get a script, and it would just be something like Penny saying, "Do you think formula to come may be a more efficient way to answer the question to come problem?" So I would just go through and give them options. And sometimes they were short, sometimes they were long. I would give them a few, especially in comedy, the lines have a meter and a rhythm. So I'd give lots of ideas. Sometimes it's things that you might understand with a high school physics class or science class. Sometimes it's something you might have no hope of understanding. And the writers would know what they want, and I would give them a few options. And this is where we came up with the idea of super asymmetry. which we'll talk about. Okay, so let's show you an example of a kind of scene that has some science in it, which I am actually I'm showing it partly because this is one of the prouder scenes I have for the science.
Then a laser will map the reflective surface and
Wow, that is amazing.
you know, there's a foundational idea in string theory that the whole universe may be a hologram.
What do you mean? Oh,
Well, the holographic principle suggests that what we all experience every day in 3 dimensions may really just be information on a surface located at the farthest reaches of our cosmos. So it's possible that our lives are really just acting out a painting on the largest canvas in the universe. What?
sometimes I forget how smart you are.
You should visit more often.
So I really love this, and I remember, I just wrote some words on a page. It's not that hard to type something into an email, and suddenly you have a whole set that was made. You have actors saying your lines, and I was off in the corner listening to the audience. And during that speech, they were incredibly quiet, and I even heard a little bit of a gasp. And so that was just a lot of fun to just see something that you just typed suddenly come to fruition. And again, you can ask, what is this scene about? You might think it's about the holographic principle, but really there was a hole in the story where a boy is trying to win back his girlfriend, and that kiss is where they get back together. And so that's the story that came along, and there's just a little science-sized hole in it. And that's how we worked. It was never really my pushing along, hey, let's do this particular type of science. There was usually always a human story, the science-sized hole in it, and then we would fill it. So then the biggest science problem of all was, what are they going to win a Nobel Prize for? And the head writer, Steve Holland, here will give a little example of what the challenge was here in the final seasons. And this is going to be just audio on National Public Radio.
Sometimes we say things to him like, Sheldon and Amy need to have a discovery that could be worthy of a Nobel Prize, but can't be something anyone else has already thought of. So go.
Right. So now we had to figure out what was a theory that is Nobel Prize winning that thousands of theorists have not thought about before. Luckily, I didn't have to have the actual theory, but it had to be close.
Sometimes.
So we started with the name. I had actually been thinking about this for months, and I was really kind of sweating because I knew this was coming. They gave me a heads up much farther in advance than I would normally get. And somehow it popped into my brain. We've talked about supersymmetry for decades in my field of particle physics. We still hope this is going to be leading us to the theory of everything. And then the idea of super asymmetry just came into my head, and I was excited, and I was like, there's no way the theorists have not come up with this theory already, a name. The theorists like little funny names. Nothing was on the preprint server, which is what we call the archive. So great, we had the name. I did tell the writers that you can't get a Nobel for a theory without an experiment. It has to be proven. And they took that opportunity to build story, because they entered 2 Fermilab kaon physicists that will prove the theory. But now we have conflict, because who is going to win the Nobel Prize? And you might think, oh, well, all 4 of them would get it, and then the stakes are not very high. But I told the writers, only 3 people can win a Nobel Prize in physics. So suddenly, we solved the problem. We had an experiment that proved it, and we had some antagonists. And suddenly, there's a story. And that's how things came together. And it's really fun to sort of understand how story works. Anyway, if anyone wants to know, there's a vague idea of normally in supersymmetry, we have to explain why the world we see around us doesn't have the partner particle that supersymmetry predicts. And so inside that theory, there's always some way to break it. It's called symmetry breaking. And the idea of Sheldon and Amy's theory is we will just skip it and we will just say it's fundamentally asymmetric to begin with. That's why it's called super asymmetry. I've now given the theorists a great idea, and so I'm just waiting. I don't know why this is not a published theory yet. So we were really proud of bringing women into science on the show. In the very beginning, we didn't have as many main characters that were women in science, but here we are. We got to the point in the show where a woman, Amy Farrah Fowler, is winning the Nobel Prize.
Thank you, Majesties. Thank you to the Nobel Committee. We are deeply honored. I would just like to take this moment to say to all the young girls out there who dream about science as a profession, go for it. It is the greatest job in the world. And if anybody tells you you can't, don't listen. And now, speaking of not listening, my husband, Dr. Sheldon Cooper.
So anyway, it's a wonderful speech. I'm so happy that this encouragement for women to join physical sciences is broadcast. About 20 million people saw it the first week. Who knows how many tens of millions more are seeing it around the world. It's really a wonderful speech. Of course, it ends on a funny note, a silly note, because that's just the way comedies work. But we were really happy to get to this point after 12 years. And this has to be an earned moment. You can't just make this scene out of nowhere. There was a lot of work and character development that brought us to this point that made the scene meaningful.
Thank you.
The cast and crew have been wonderful to us. If you see these young people here, these are the Big Bang Theory scholars at UCLA. Through donations, personal donations from the writers and the actors and others, there are 10 full tuition STEM scholarships that exist in perpetuity at UCLA, plus another 20 that kicked it off. So that's really exciting, and I meet them from time to time at UCLA. So in addition to being encouraging on the show, in real life, the show is supporting young people in science. So early on, we wondered if this could be educational. So let me show you a little clip and then a follow-up I had by some email.
So how'd it go with Leslie?
Oh, we tried kissing, but the Earth didn't move. I mean, any more than the 383 miles that it was going to move anyway.
Well, okay, so that number is a number, that 383 miles was not in the original script. It's one that I put in there. And then I got an email from a young woman named Olivia. And I'll just read the parts in red. I'm a sophomore in Barrington High School, it's near Chicago, and I'm a huge fan of the Big Bang Theory, which was great because it was the first season. Leonard asked Leslie on a date, but she proposes instead of accepting the invitation, they kiss and see how it works out. And then he mentions the 383 miles it would have moved in about the 1 second for a kiss. Then she says she's very puzzled. And there's a whole calculation she sent me about the 34.88 degrees latitude, the Earth is spinning at a certain radius, and so forth. So I responded, I pointed out, oh, she kept going, and then maybe she meant that Leonard meant that not the rotation of the Earth, but the Earth going around the sun, which is even faster. It's closer, but not even close to correct. And, thank you for your help with this. So that's actually not how I made the calculation. There's another parameter that people haven't considered, that she hadn't considered. Not only is the Earth revolving around the sun once per year, but the sun itself is revolving around the center of the Milky Way galaxy, around this giant black hole. And that's called the galactic year, and it takes 250 million years. And most of our speed comes from that. And then she wrote back, fantastic, and she figured it all out, and she got remarkably close to the right answer. I cannot say that I did the calculation this way, but I was not going to argue with her for getting the right answer that close. Now, of course, you could ask, what does it even mean to have a speed since there is no absolute reference frame to compare it to, and speed is relative, but that was a higher level question. So the show is over. I'm really sorry about that. But we actually have earned making a character over these 12 years. There is a prequel, it's a show about Sheldon when he's younger, around 1989, 1990. I think we're up to 1991. And there was a really wonderful moment at the end of season 2. And if you're not yet watching this show, but you like The Big Bang Theory, I would encourage you to tune into this. It's really a sweet show and very funny. And so here is, for those people that knew all about Big Bang Theory, and this is taking place back in 1990. It's a wonderful episode. They asked me, how could Sheldon watch the Nobel announcement, the Nobel Prize announcement back in 1990? There was no World Wide Web. There were no web browsers to tune into. It wasn't going to be broadcast on television in pretty much anywhere in the U.S., let alone remote rural Texas. So I suggested shortwave radio, and that's what he's listening to here.
The announcements are starting. You want me to stay? I'll be in my room if you need me.
Citation in German, French, and Russian. And this year's Nobel Prize in Physics is awarded to Henry Campbell, Jerome Friedman, and Richard Taylor for the discovery of quarks.
A primary feature of quarks is that they're always bonded together. But in that moment, I felt like a neutrino, destined to be alone forever.
Leonard, dear, you should be in bed.
Just as you, my baby, there's stuff when say. Yes, we will. Howard, turn off that macaque game and go to sleep.
Thankfully, I was wrong.
So yeah, that was really, I thought really sweet. And again, it gets back to what is this show really about? So I'll let you think about it. In the end, this show and the prequel, Young Sheldon, as much as I like to think about their science, it's about science. It is about a lot more than that. I can't really give you an answer, but I do have a little audio recording of Bill Prady, co-creator and co-executive producer of the Big Bang Theory, where he was being interviewed at the moment of the last week of the series Big Bang Theory.
All of the people who have said that they see themselves in the show because they were outsiders and people who didn't fit in. That was me. All of the people.
So anyway, I want to thank you for having me here at East Texas Tech University. Of course, that's a joke. East Texas Tech is where Sheldon goes to college as a youngster in young Sheldon. So thank you for having me here at Texas A&M. And I think now we're going to move on to some questions, which I always love answering.
Yes, thank you so much, Dr. Saltzberg. We've got a few questions for you here. So for the first one, we have from Chelsea. How hard is it to be a science consultant? Do you need a PhD?
How hard is it to be a science consultant, and do you need a PhD? I would say that it helps in that I am an actual practicing scientist, that there's a certain level of nuance, I think, of knowing what people might really say and what they might really do, and which is what the writers, I believe, want. and the actors too. I think their actors are really good at playing make believe. They don't need me really, but I do think it helps a little bit that they know the words on the page are not going to sound silly, hopefully, to a scientist. And so it isn't so much the PhD so much as that I'm actually involved, I think, in day-to-day science. And what allows me to go there is having a PhD, which is kind of your license to do science as a professional. So that definitely has helped. And again, like in neuroscience, I don't have a PhD in neuroscience. So I do need to talk to people that do have PhDs in neuroscience or do have experience doing science day to day in order to make sure it sounds right. Now, Freeman Dyson, the famous physicist, actually never had a PhD, and it didn't hold him back. That would be pretty rare. The standard entry into doing science day to day is with that PhD.
Wonderful. For our next question, we have from Dino Girl. Why is the expansion of the universe expanding?
Why is the why is the universe expanding? Why was there a Big Bang? That is the title of our show. There is a theory called the Big Bang theory, not the show, but the theory of explaining why the universe is expanding. And it was actually originally derogatory. Back in the turn of the 20th century, 2020s, people thought maybe the universe was static, that it looked like what it looked like now forever. It turned out when Albert Einstein and others were putting together the theory of general relativity, they saw the universe naturally wanted to expand or contract, which meant physically space would be created and stretched or shrink. And that didn't even make sense to them at the time, and they found a parameter to get rid of it. Then Edwin Hubble and others found that, in fact, distant galaxies were receding from us. We can see that by a kind of a Doppler effect. If you see a train heading away from you, for example, and the sound, you can hear that gets lower, and the same thing happens with light. So it's a what came first, I would say, is the realization that the universe is expanding, and then understanding that the equations that we believe describe the universe allowed it. So it fits in, we understand the theory and why, and the observation, it all makes sense. Now, why this is the particular theory that our universe follows and not some other law of physics, I think nobody knows. But it is an empirical fact, and it is explained by the best theory we have that the universe is expanding.
Gotcha.
Looks like it will continue to expand forever.
Yep. For our next question, this is from Anthony. How long will young Sheldon be planning to go on for?
Well, it's an interesting. So we just finished the 4th season, which is 4 years, and we just found out last week the contracts were signed for 3 more years. So it's at least going to go through season 7. Knocking on wood, as long as nothing unpredictable happens.
Awesome. Our next question is from Seth the Cat Productions. Has the show changed the way you teach?
Has the show changed the way I teach? That's I do have a little more feeling for showmanship or showpersonship. The idea that humans really do react to stories, that you can get someone's interest with a question, that a story has a beginning, middle, and an end. And so when I do have lectures, which I teach, large, sometimes I teach large, what we call lower division, introductory physics, F equals ma, Faraday's law. I do try to structure my lecture a little bit like a story and have it fit. I have a little more understanding of how people react to stories. I also know how hard it is to make a story, having watched these writers. So I can't say that I really succeed all the time.
Yeah, I can agree with that. It's pretty tough trying to put that kind of stuff together, but I can also see how that sort of story-taking approach will keep people hooked into the conversation. Our next question here is from The Annoying Apple. Do we need new mathematics to explain the asymmetry in our universe?
Do we need new mathematics to explain the asymmetry in our universe? And there are many asymmetries we observe in our universe. For example, why is there so much matter and not antimatter? You might think the equations that describe everything are symmetric. Where is that coming from? And people have ideas. I'm just going to think about changing the question a little bit. Mathematics is the language we use, but the ideas are physics. So I would phrase the question, do we have to change the physics that we use? And I would say almost everyone believes the physics we have, which is expressed in the language of mathematics, but the physics we have, although it explains everything we have pretty well, we don't believe it's the final story, that it's really the deepest explanation. If you go back to, say, the 1880s and 1890s, the periodic table of the elements was discovered. Probably anyone who's ever been in a science classroom has seen a poster of the periodic table of the elements. There's all these amazing patterns in there, rows and columns of how elements, for example, helium behaves a lot like neon, behaves a lot like xenon. Why is that? At the time the periodic table was put together, we now know they had no hope of understanding why that was true. Since then, and then following decades, quantum mechanics was developed. People understood more about spectroscopy. And we now understand very well about the way atoms are put together that gives you a periodic table. Well, we have all sorts of patterns that we see now among our data. We have asymmetries, for example, the matter and antimatter asymmetry. There's other kinds of symmetries that are broken a little bit or a lot that we don't understand. And I believe we're in a situation like these people that have the periodic table. We have the data, it's going to be explained by something, but we don't yet have that physics that's going to explain it, but we will get there.
Awesome.
And the next generation, if they're watching, maybe they'll be the ones that do it.
Hopefully so. Maybe this will inspire them to pursue such efforts. Our next question is from Jesus. Is the beginning of the universe also the beginning of time? And as time expands forward, could it also expand backwards?
So we're talking about the origin of the universe, which is becoming a bit speculative. So you can talk to a lot of people and they'll all be convinced of an answer, but they'll be convinced of different answers. It's a wonderful question in that it kind of assumes that we all know even what time is. And if you start asking yourself, what is time? You start to get a little confused. Probably the best explanation of what I heard, what is time? Probably the best answer I ever heard was, time is what keeps everything from happening at once. So we don't really know. Was there something that happened before the Big Bang? Is the Big Bang the creation of space and time that we have now? Did that come out of something else? We don't know. People write papers thinking they know or speculating. There could be an idea that, in fact, two universes were created at once, one going in the direction of time that we know, another going in the direction of time in the opposite direction, keeping things symmetric. But because they all start in a low entropy state or a state of high order and go forward in that direction, eggs get scrambled, eggs don't get unscrambled. Both observers in different universes, even though perhaps it's going opposite along some sort of meta-time axis, would both see time going in the forward direction. Who knows? This is all just speculation. In the end, I'll get back to this again. It's physics, not mathematics. We only know what we know if experiment says so. And so we don't know what experiment to do to look for other universes or look for what happened before the Big Bang, if that's even a meaningful thing to say.
Awesome. Our next question is from Optimistic. Do the actors need to learn physics concepts before acting out in preparation for the scenes?
So the actors don't really want to know a lot of physics, and I don't blame them. They do want to know that it's real. We play some tricks to make it all seem kosher. For example, when Sheldon is writing an equation, if you look carefully, you don't really see him writing the whole equation. You'll often see him just finishing the equation. So the equation was written by the prop master, and then he's got 3 copies of that board. And then each time the scene is shot, Sheldon, played by Jim Parsons, would write sort of the final parenthesis or the final X. And so in your mind, it looks like he just wrote that whole equation. But if you look carefully, he didn't really. or experimental work with Leonard. It's pretty, usually the actors don't really need me. And they, as I said, they're really good at playing make-believe. That's what their profession is. But for example, Sheldon was working at one of the optical tables with some screwdrivers and some bolts. And so Leonard, I'm looking at it, Leonard was doing it. It was played by Johnny Galecki. And he asked me, what am I doing with my hands? And I could have said, well, it doesn't matter, do whatever you want. But that makes more work for him because now he has to come up with something that makes sense and then he has to remember it. By my telling him, pick this up with your right hand, turn it a quarter turn and put it over there, immediately gets into his brain, is the way I think it works. And he's doing many other things at once. In addition to saying his lines, he's standing in a certain place, he's looking at certain people, he's projecting certain emotions and states of mind. So we do work a bit on understanding science, whether it's the theory or the experiment, but it's just part of what's going on. They just need to know enough to have you believe that they know what's going on.
Gotcha. Do you ever just let them wing it sometimes?
What's really interesting about our show is essentially every word they say is the word on the page. If they change even one word, often they'll just do a retake.
Gotcha.
And there's a reason for that. Jokes have a definite set of timing.
Mm-hmm.
One of the co-creators and co-executive producers, Chuck Lorre, was a musician before he was a comedy writer, and I think you can sort of hear that if you listen to the rhythm. So changing a word or two actually can take a funny joke and make it not funny. And certainly with all the science in it, they're not about to change the words. And so the actors are bringing a lot to the table. As I said, where they're looking, where they're walking, how they're projecting, how fast they're speaking, if their emotion, how angry they are or not. Incredible amounts of things to tune, but the actual words are what the writers give them.
I see. Our next question is from Rohan. Is space connected to time?
Is space connected? In fact, well, we talk about space-time because we think of them as one thing. And that goes back to the experiments and the theories of Albert Einstein in 1905 or so forth. It's stuff that Alexei and I use every day. That somebody might, you might look at two events, like someone pushes a button and then there's an explosion. You might think of these two events separated in space and in time, right? There's a place where you push the button and a place where the explosion happened, or there's a moment when someone pushed the button and a moment where the explosion happened. But if you were going past this little story I just told you in a rocket ship, you would see a different distance between these events and a different time between these events. And it turns out the mathematical structure to describe them that makes sense is actually called space-time. There are formulas about the distance and the time between these events that do stay constant between people in rockets and people who are not. And so it's been learned pretty early on that space and time are really two aspects of the same thing, something called space-time. And this is not speculative. This is something that we use every day.
Yeah, it's very interesting the way you put it, because the mathematics for it make them act almost identical to one another, but it's just so very different in your day-to-day life.
What's interesting, for those who are going to learn some special relativity, what's pretty interesting, again, mathematics versus physics, the mathematics of special relativity, when you're going to learn it, there's nothing more complicated than products and square roots. So the mathematics of special relativity is not that daunting. A few little diagrams that are helpful, but the physics is really kind of tough. It takes our students a few weeks or months to really get their heads around it. So again, it's an important point. It's been coming up a few times. Physics is not mathematics. Mathematics is our language, but physics is something more than just the math.
Yes, I agree. Our next question is from Yoon Park. Do you like teaching?
Oh yeah, I love teaching. And I just finished teaching an electronics course, and even though it was teaching remote, we got everyone oscilloscopes and electronics, and it was really great to pop into the Zoom rooms and help people debug things. It was wonderful because in that case, I know where the students are at the beginning of the class, and that's always key, and to bring them to the next place is a wonderful thing to do and see. But I get asked that question a lot. And of course, if you ask me at the moment, an hour before the lecture, when I don't have a lecture ready and someone's calling me on the phone and someone's emailing me because they need a budget in the next hour, and I also don't have a lecture in the next hour, if you ask me if I enjoy teaching at that moment, I probably would give you a different answer. But overall, thinking about a career, teaching is a wonderful thing to do.
Wonderful. Our next question is from Nia. What do you think about the multiverse theory?
What do I think? So what about the multiverse theory, which clearly means multiple universes? But what does it really mean? People use that term, I think, in a lot of different ways. One is, well, maybe our universe, which has 3 space dimensions and 1 time dimension, maybe it exists in some larger space, multiple dimensions, and we're just seeing a piece of it. And maybe that's, our Big Bang that created our universe was a little bubble in a higher structure. That's possible. Could be. There's no evidence against it. People use the word again, and we used it in the Big Bang Theory as an interpretation of quantum mechanics. There's a lot of trouble in quantum mechanics. We're not going to go through a huge lecture, but when you observe something, things happen. And how do you deal with this observer and the experiment, and how do you describe what happened? There's many descriptions. They all give the same answer. But one of those descriptions is, well, at the moment you make this measurement, we split into 2 universes, and one had one outcome and one had the other. And there are reasons to like this interpretation. I don't know that we'll ever be able to prove that that exists. So this idea of multiple universes comes in a lot. And who am I to say that it's wrong? Because the history of science is all about learning that our place in the universe is smaller and smaller, that the universe is bigger and bigger. We started with just understanding the Earth. Then we learned the Earth was actually part of the solar system, which is really pretty big. And then we learned that the solar system is just one star in a galaxy, which is an even bigger structure. And then we learned that there are other galaxies just like ours or slightly different. And then we learned that there were clusters of galaxies. So as time has gone on, the stage on which we see science unfolding is getting bigger and bigger. So if we were to find out the universe is really just one, and there's actually a multiverse, well, that would be consistent with how everything has unfolded so far.
A hard thing to imagine, but yes, that would be amazing. Our next one is from Sequoia, and they say, I'm interested in acting and I also love STEM, specifically biology and zoology. What would you recommend I do in my career?
Wow, that's really interesting. So Maya Bialik has done this. She was an actor as a young adult, and then later went on to get a bachelor's and PhD in neuroscience, and then came back and do acting. But not that her path has to be your path. I don't know what to say other than follow your dreams. Opportunities will come, hopefully. This is a tough question to answer. It's a question of how to live one's best life and do the best you can, I think is all we can really say. Try to keep as many of your interests active as you can at once.
I think that's wonderful advice. This last one that we have is from Shub. After Young Sheldon, what are you going to do? Are you going to be on another show? And if so, which one?
Well, people joke about, old Sheldon, and maybe there'll be an old Sheldon that's a sequel to the original show. Who knows? I have been really very fortunate that my particular expertise matched pretty well to this show. It was the kind of physics that I know, also didn't go super deep. It was, we had a lot of different science, but we never went really deep into it in the same way that if you watch the movie Interstellar, the science consultant there was Nobel laureate Kip Thorne, who invented a lot of the ideas, the real scientific ideas, and even wrote a book all about the science behind Interstellar, very deep. So I am not, any given science story that comes along, the chances are I'm not the right person. So I've often gotten questions about getting involved, and I'm one step away from the person that is the right person. And so I often connect people to shows. So this was just a wonderful, miraculous thing that happened to me in my life. I met fantastic creative people, dedicated people. I've learned a lot. I would be surprised if there's ever another show after Young Sheldon that fits my wheelhouse. So, and I'll just accept what a great time it was.
Thank you so much for those questions. We'll go ahead and carry on over to Dr. Safna.
All right. Well, I guess, from all of us at the Eastern Texas Tech University, thank you very much, David, for this very interesting and engaging presentation and the follow-up questions and answers. So I would like to use this opportunity to invite you to come again to Texas A&M as soon as travel becomes safe again, with either a seminar or a colloquium you can choose. And we also would like to thank all of our guests and of the festival for their support for research and science. So stay well, stay safe. Thank you.
Everybody loves bubbles. How could you not love bubbles? Look how fun they are. I mean, come on, they're so much fun.
Hey, Nicole.
Hey, Chelsea.
I bet you I can make your bubbles even more fun.
There's no way you can make bubbles more fun than this.
Well, my bubbles can float in midair.
Okay, you're right. That sounds like so much more fun.
Here, let me show you.
Okay. Oh my gosh, they're actually floating there. They're not touching the ground. How do you do that? Do you have like magic bubble juice or something?
No, Nicole, it's not magic. It's physics.
Oh, of course it's physics. We're in a physics festival.
You see, before I blew these bubbles, I filled this tank with solid CO2, also known as dry ice. And dry ice sublimates, which means it doesn't have a liquid phase like water does when it melts. It goes straight from being a solid to a gas.
Oh, I see. So now this whole tank is filled with CO2 gas. And that CO2 gas is heavier than the air that you were blowing in the bubbles. So the bubbles float on top of the CO2.
That's exactly right.
Oh my gosh.
We hope you guys enjoy the rest of the festival.
For this demonstration, you need a lot of courage and faith in the laws of physics. I have here a paper cylinder left over from a roll of toilet paper, and I have a raw egg. I will mount this raw egg on the top of the cylinder. The cylinder is on the plate over the glass with water. Now this courage and faith part come. I will hit this plate with my hand, and I will hit it hard without hesitation. If I do it right, then the plate will fly, the roll will fly, but the egg will not fly. It has inertia, so it will just fall into this glass with water. If I lose my confidence in physics, then and I don't hit it hard enough, then this plate will fly too slow. The egg will fly away, and I'll create a mess. Let's see what I can do. Ready? 1, 2, 3.
The air around us is mostly nitrogen. So you can think of liquid nitrogen almost like liquid air. Does this mean that we can freeze air into a solid with liquid nitrogen? Obviously not, because the freezing temperature of nitrogen is lower than the temperature of liquid nitrogen. However, let's watch what happens when a glass of liquid nitrogen is put under a bell jar. Under this bell jar, a vacuum pump can suck out all the air in a matter of seconds. Watch as our once liquid nitrogen turns into a chunk of slushy ice. We just made solid air. But how did it happen? Evaporative cooling. This is what happens when you sweat on a hot day. The moisture evaporates off your skin and cools you down. When the liquid nitrogen boils, its fastest molecules leave the surface. Now, after we turn on the vacuum, we're taking away the fastest, most energetic nitrogen molecules, so this liquid cools down to the point where it turns into a solid. Look, I bet you thought you'd never see solid air. This is a slushy you could order on the freezing planet of Neptune.
Howdy. Now let's use physics and electricity to create some lightning. There are two sabers here. These sabers are used by the Corps of Cadets, and seniors in the Corps use these sabers at important events such as football game marches. Although the sabers that we have here have seen more war than the ones that the seniors actually use. The Corps of Cadets is the largest student organization here on campus, and cadets are known as the keepers of spirit and guardians of tradition. Now, do you see this button there? People say to never push the red button, which is why we made this one green. Did you see that? A spark was formed between the two sabers. Now let's try to understand what exactly happened here. When I pushed the button, a high voltage was generated. This voltage was so high that it ripped the electrons from the air inside and converted it into an ionized plasma. The ionized plasma is such a good conductor that it allows electricity to flow between the sabers. This shorts the circuit, and therefore you can see the spark. The spark is formed at the bottom because the strongest electric fields are created where the distance between the sabers is the shortest. And since the ionized plasma is hot, this spark rises upwards. Eventually, the distance between the sabers becomes too large for the plasma to be conducting, and the spark disappears. Let's see it one more time. This is exactly how lightning works. There's a high voltage that's created during thunderstorms between the clouds and the ground. This voltage is so high that a bolt of lightning is discharged, and that's how lightning occurs. Let's see it for one final time. Now, we do use sabers in wars, but do you know what else we use? Cannons, which is why we have Nathan with the Galilean cannon next.
Howdy! We all like collisions, right? What about cannons? Why not both? Here in this demonstration, we have varying size balls that get smaller as we move away from the base. What do you think will happen if I drop this ball from this height? Didn't really go that high. That's because the energy of the falling ball is transferred to heat as soon as it hits this ball. What do you think will happen if I drop both of these balls at the same time? Do you think it will go higher or lower? Let's find out. So here we can see that the ball went slightly higher than it did originally. But now, what do you think will happen if we drop all these at the same time? How high do you think it'll go? That's so cool. So the reason why the combination of balls goes slightly high, or much higher than it did originally, is due to a thing called conservation of momentum. As all the balls are falling at the same time, once this big ball bounces back up, it gives the next ball an extra kick. We say that the big ball is giving some of its momentum to the smaller ball, and this happens until most of the momentum is in the smaller ball, sending it flying. We can do this exact same demonstration at the comfort of your own home with a basketball and a tennis ball. So what we learned about conservation of momentum, if I put this ball on top, we could send this flying. Yeah. Oh, and they came back. So I really hope that this simple demonstration expanded your mind about physics, but if not, our next demonstrator, Carlos, will.
Hello. When you think of shaving cream, what comes to mind? Soft, light, and puffy? Well, shaving cream is mostly made up of a few ingredients: soap, glycerin, foaming agents, and air. Lots and lots of air. In fact, air is what gives shaving cream most of its structure. We have air inside of this cream, pushing it out and giving it that soft little fluffy shape we're very familiar with. But what happens if we were to take air out of the shaving cream? Well, with this vacuum pump and our bell jar here, we can do exactly that. Let's add in some colors to spice things up a little bit. And now we can take out the air from this bell jar. As we turn it on, we'll be evacuating the outside atmospheric air from this chamber. As we do that, the inside air of this shaving cream is going to expand that shaving cream and push out, now that we no longer have atmospheric pressure holding it in. And it's going to expand and expand and expand. What do you think is going to happen when it reaches full expansion? Well, it really expanded. But what's going to happen when we turn off this bell jar and vacuum pump and the air back inside? Will it stay the same shape? Wow, it really fell flat. But why did it fall flat? Well, as the outside air started coming back in, the inside air that had been holding the shaving cream structure had also been evacuated, along with the rest of the atmospheric pressure. With no more internal air to hold this internal pressure, this outside pressure collapsed the shaving cream back into this liquid state, the same state it's in the cans actually. I hope you enjoy this demonstration and the rest of the physics festival.
Earlier, y'all saw how we could visualize heat directly with FLIR. FLIR showed things that were hot as bright white, things were cold as cold blue. But there's another way we can actually visualize changes in air. You might know before that hot air becomes less dense and rises, and cold air becomes more dense and cools. But it also actually changes how light interacts with the air. You have seen this before if you've ever seen a mirage. Say hot wavy lines coming off of a desert reflecting a lake from the distance, or possibly just coming off of your very hot car on a summer day in Texas. However, with this demo, we can really accentuate that. This is a Schlieren optics demo. It's designed to emphasize every little change in how air refracts light. We have here a telescope, a parabolic 13-inch telescope mirror, and on the other side we have a camera with a knife edge filter and a pinhole light. And that allows us to really visualize changes in density air. For example, if I take this lighter and light this tea candle right in front of the mirror, we should see a glorious bloom of hot air rising up. You might even see it's narrower at the bottom, and then it becomes turbulent as it flows up and becomes non-laminar. But we don't just visualize hot air. We can also visualize cold air falling. For example, here I have some dry ice. If I take a chunk of this dry ice, which is just solid CO2 and I hold it in front of the mirror, you should see cold air sinking off of it. Now, dry ice is pretty cold, but I have something even colder. So cold that I need to put goggles on for safety. In this second styrofoam cup, I have liquid nitrogen, and this stuff is very cold. If I come over here and pretend to pour out a little bit, or not even pour out a little bit, just the cold air on top, you'll see, ooh, I actually did pour out some of it there. You'll see cold air falling out of the cup. But this setup doesn't just visualize change in temperature of air, because other things can change how the index refraction of air works or the density of air works. For example, ordinary isopropyl alcohol. This stuff you might know has noxious fumes which you don't want to breathe in, but those fumes are also different with index refraction. So if I put it in front of here and poof it a couple times, you can actually see plumes of it coming out of the bottle. This sort of demo in the real world is actually used to visualize, say, hot air flow through a building or other things like shock waves around supersonic jets. But in here, we can use it just to show some cool stuff. I hope you've enjoyed this demo.
Here is the famous Texas A&M square-wheeled bicycle. That being said, you probably don't want to enter it at any races anytime soon. Move! They say you shouldn't reinvent the wheel, but here at Texas A&M, we did just that. Not only did we reinvent the wheel, we reinvented the ground as well. On our special track, the square-wheeled trike is in its natural habitat. So much easier. The shape of this track is called a catenary, or an inverted hyperbolic cosine. It's the same shape a heavy chain makes if you hold it by both ends, only upside down. Not only that, but catenaries are good at supporting heavy weights, so they're often used in the design of high ceilings and bridges. That being said, you probably should stick to your normal bike on normal ground for everyday use. But please, when the pandemic's over, come check out our Texas A&M square-wheeled bicycle. It's pretty great.
Howdy everybody. So this demo here was built to showcase a little something called Lenz's Law. So let's take a look at what I got here. I've got 5 different rods made of different materials. So I've got 2 rods made of aluminum here. I've got a rod made of copper. I've got a rod made of brass, and I've got an acrylic rod in the middle here. And around each of these rods, I've got a little ring magnet suspended there. All right, so let's talk a little bit about what's going to go on here. So in this festival, you may have heard of some concept called induction. And I know that sounds fancy, but all that means is that a changing magnetic field can induce a current in a conductor. So in this case, we're going to be inducing eddy currents. And what's really, really cool is that these induced currents actually have their own magnetic field. And this is where Lenz's law comes into play. Lenz's law tells us that the direction of the magnetic field made here is opposing the change that created it. So that's really cool. It's almost like these conductors don't want to change their magnetic field. They're pushing back against the change that created it. And the strength that they push back is going to be related to how good they are at conducting electricity. So what I'm about to do here is I'm about to drop all of these magnets from the top of this board. And what do you guys think is going to happen? Well, let's check it out. Pretty cool, right? So as you saw, the magnet around the acrylic just fell and hit the ground like nothing was there. Whereas the ones around these metal bars kind of, floated on their way down. And especially the magnet around this copper rod took its real nice time getting down there. So what does that tell us? That tells us that this acrylic rod cannot conduct electricity. There was no eddy currents going on there. Whereas this copper rod had some really strong currents pushing back against that magnet falling down. And that makes sense, right? You don't see your wires made out of acrylic, you see them made out of copper. Well, that's Lenz's Law, guys. I hope you guys learned something today and in the rest of this festival. And thank you, and gig 'em.
We have 2 balloons here. If we pour liquid nitrogen on both of them, which will shrink first? Of course, the maroon balloon would win. I mean, we are Texas A&M. But because this is science, we can always predict the outcome. So, how did we know that the maroon balloon would deflate faster? Well, we filled the maroon balloon with pure oxygen, and the other balloon with air, which is mostly nitrogen. Because the boiling point of oxygen is higher than that of nitrogen, all the oxygen was condensed into a liquid. Have you ever seen liquid oxygen? If not, you're in luck. We're about to make some for you using the difference in boiling points. We'll be using liquid nitrogen to help us cool the oxygen into its liquid phase. Let's look what happens when we pour liquid nitrogen over the magnets. They get cool, but nothing sticks. Now, let's pour liquid oxygen on them. The oxygen sticks to the magnets. This is because the oxygen is paramagnetic, so each molecule is like a tiny magnet. When it's cooled down into its liquid state, the molecules slow down and are able to exhibit their magnetic properties.
Imagine that you work at the International Space Station and you want to go for a spacewalk. What will happen with you if you don't wear a pressurized suit? I can recreate these conditions here. I have a marshmallow guy. What is marshmallow? It's sugar and a lot of air. I have a bell jar and I have a vacuum pump. So right now we have here smiling marshmallow guy. There is equilibrium. Pressure from outside is the same as pressure from inside. Now I will cover this marshmallow guy with my bell jar. Oh, marshmallow, please go in. He doesn't want, but that's fine. It's just a coat. Is he smiling still? Okay, now I start pumping air out of my bell jar. I switch my vacuum pump. Watch. I'm pumping out air. No pressure from outside, same pressure from inside. Marshmallow guy is expanding. Now it's a big marshmallow guy. What will happen if I switch off vacuum pump and I will let air in? Now watch. Never go for a spacewalk without pressurized fluid. Enjoy the festival.
Howdy. I'm here to tell you about one aspect of our glorious universe. The whole shebang is made out of atoms, every last bit of it. And those atoms, each and every one of them, is a tiny solar system. It's got a positive nucleus and orbiting electrons around it, electrically charged. We can tear those atoms apart with technology to rip off the electrons, and they can then carry current and make electricity and all the things that you know of that you use and have pleasure with electricity. I'm going to show you a particularly kind of interesting example of how we pull those electrons off and make electricity with a bit of an effect. It's called a Tesla coil. So here I'm going to energize it and get it going, and we'll crank it up, and so that I'm getting more and more voltage to the coil of the Tesla coil until finally it begins ripping atoms apart. That's how we rip atoms apart and how we accelerate the electrons that we rip free from the atoms until they have enough energy, they ionize more atoms and make a lightning bolt. So you can see those lightning bolts when you go out in a thunderstorm, although you ought to be careful. And you can come to a particle accelerator where we use that same kind of lightning to study the fundamental properties of matter down inside the nucleus and inside the quarks and leptons. Life is fun, physics is great. Thank you much.
what I'm doing here is, well, we have a motor attached to this tube and it's spinning. And this piece right here is a tensioner to hold the wire taut so that it stays even and everything. And I'm just watching it to make sure that it doesn't ever cross over. So once we have the wire, I'll call it up. Obviously, so this is the past one. So we're gonna put it on this block, on this E right here. And then we're gonna end up covering it, and the plastics are to reduce the air gap. And then we put this this other block on top. And this is going to help us regulate the current that's going to go into our Tesla. So we are building the capacitor bank for the Tesla coil. Each one of these plates is going to have 28 capacitors and 28 resistors on it. And it's going to have a total of 45 kilovolts across all 28 of these. And what's the total capacitance going to be, do you remember?
I think it's 0.1 microfarads.
Yeah. So, big capacitors.
Nice.
Soll ich es dafür anzünden?
Now we're clear.
You've all been asking wonderful questions. Let's go ahead and take care of some of them. First, we have Adrian Thompson.
Hi, thanks very much for your questions. So I saw one in the chat that not just one person was asking, but actually several people. They were asking if lightning is hotter than the sun, or is lightning the hottest thing around? So surprisingly, and I had to look up the numbers on this, lightning can actually get up to temperatures hotter than the surface of the sun, which sits around 6,000 Kelvin, which translates to a little under 6,000 Kelvin. A little under 6,000 degrees centigrade. However, the interior of the sun is way, way hotter than lightning. It sits around millions and millions of Kelvin, if I read these numbers correctly. So that's a really interesting question. Lightning is actually hotter than the surface of the sun, around 5 times hotter. Pretty amazing, actually, that we can get up to those temperatures just here on Earth.
I probably would have guessed the other way blindly. Thank you.
Yeah.
For our next question, we have... We're still pending on that. Give me just a moment. Yes, there we go. Ryan Mueller.
Hi, everyone. I have a couple of questions here from Serenoptics that I'll try to cover real quick. From Perfect Pilot asks, can't you see the sound barrier break in Seren imaging? And the answer is yeah, it's really cool. In fact, you could even do it with actively flying planes. With backward-oriented Seren, which is a more advanced technique that's used by NASA, for example, they can take images of planes flying, breaking sound barrier, and you can see these beautiful shock diamonds, or not shock diamonds, shock waves coming off the front of the cloud. It's amazing. Jack Howell asks, does this demonstration also explain why we see heat rising up the pavement? And that's exactly right. It's the index refraction of air changing with the hot or cold air that causes the effect. So it's the exact same thing. All this demonstration is doing is just magnifying the effect so we can see it as clear as possible. And Brenna asks, is that a normal mirror? And the answer is not really. It's a parabolic mirror, or it could also be a spherical mirror. And the reason why this is the case is you can look up ray optics, and if you want to get really into the optics of it, if you put a light source at the center of a sphere, light will always reflect back to the original point. So we put a pinhole light source and a camera there, and when it bounces back and is focused right at the front of the mirror, and then that's how we apply our filter so we can emphasize the effect.
Very neat. Thank you. Next, we have Josh Winchell.
Hello again. There have been a couple of questions about liquid nitrogen I want to talk about. Yukti asked why liquid nitrogen is so important, and Yoon Park asked if there's anything colder than liquid nitrogen. So why do we have liquid nitrogen here so much? In a sense, it's just the most readily available, coldest thing we can get. You can get colder things though. You could, if you want, make it even colder, but there is, for example, liquid helium, which is often colder than liquid nitrogen. Now, why might you want that? Why would you want helium instead of nitrogen or possibly some other element? Well, so think back to some of the superconductor stuff you saw. Remember, those require really cold temperatures to work. You may be restricted to only using some particular element for your superconductor in some other experiment you're using, say. And different superconductors become superconducting at different, usually really cold temperatures. So if you have some other element that is only superconducting at some really tiny temperature, maybe liquid NOx or nitrogen cannot get you there. And in fact, depending on your experiment, exactly where that transition between normal conducting and superconducting happens can be really important. For example, you may want a particle detector to be super sensitive. If you can have it hovering at exactly its transition temperature, which will be easier to get to with some one particular liquid than another, then it will be really sensitive to anything that comes in and messes it up. And again, liquid nitrogen, liquid helium, some particular combination of liquid whatever and detector crystal will be required to get exactly what you want.
Thank you. Very neat. Next, we have Dr. Dawson.
So, Brenna Allen asked, how did the solid nitrogen puck jump up in the beaker? And what happened in there was, while we were pumping out the air from inside of that jar, we've created a vacuum, essentially. That liquid nitrogen, though, ends up somewhat still evaporating. Some of it is turned into gas over time. So what happens is we're pumping out air, we're cooling down the atoms, but not all of them are going to get cooled. So what's going to end up happening is we still create that nice solid nitrogen disk, but there's some air underneath it, which just kind of pushes it up a little bit.
I see.
So there was also another question by Yoon Park, I believe. The question was, can the Tesla coil make a fire? The answer is yes. It's extremely dangerous, and you do not. You have to be very careful in how you put that together and where you situate it, so that way you don't cause any sort of stray bolt of electricity from causing something to start burning.
Great advice. Our next expert will be Dr. McIntyre.
Howdy. Several people were asking questions about what's the best conductor. Is it copper, or is it aluminum, or silver, or gold? Those are all good electrical conductors. Their limit is always that the conducting of electricity is using the electrons that are in the outermost shell of each of the atoms, and as they're delocalized from being bound to one atom or another atom, but are there as a kind of a sea that can move if there's an electric field that exerts a force on it. So that motion, though, like any object moving within a bunch of other objects, makes them collide with the atoms that they are more or less free to move in. Every time they collide, they lose some energy, and that's electric resistance. There's just this absolutely amazing property of Mother Nature called superconductivity that is capable of making that resistance disappear. Not just get very low to make the best conductor, but a perfect conductor, a conductor that loses no heat when current is carried in that material. That happens in almost a juggler kind of a way. As an electron feels an electric field from potential difference between two places on the superconductor and begins to move, the quantum mechanics that determines the possible ways it can move limits it by coupling it to the other conduction electrons that are nearby, so that they couple up as pairs. We call them Cooper pairs. And they have this really amazing property in which the two Cooper paired electrons interact as they're moving through the lattice. And yes, they do scatter from the atoms that are there, but they can't lose energy because they scatter in a way that's locked by quantum mechanics, so that each time atom A of the pair scatters that way, atom B scatters exactly the opposite way with the same momentum recoil. So in that, there's no change in the momentum, there's no change in the energy, and there's no electric resistance. And that is Mother Nature's juggling game. Works beautifully so long as the temperature of the material is cold enough, as my friend said, so that those Cooper pairs can stay bound together. So those are really pretty materials, and we build magnets with.
Awesome. Well, with that, we thank you so much for being a part of the festival this year. Once again, we'd like to thank Halliburton, Colonel Halshade, Class of 67, and our Spirit of Giving crowdfunding donors for making this year's Physics Festival possible. Soon, we'll provide a link to all the Zoom rooms on our website, as well as a handy QR code for those of you that are watching from your smartphone. Please stay tuned as we share our grand finale for this live stream, a fantastical 5-barrel depth charge.
Bucket one.
Bucket one!
Bucket two.
Bucket two!
Follow.
Follow!
Cup one.
Cup one! Cup one!
Cup two.
Cup two! Cup two!
Cap.
Cap! 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 Fire in the hole!
Fire in the hole.
Fire in the hole!
What are you waiting for? Go to tx.ag/festival schedule or scan the QR code on the screen and interact with scientists and more demos via Zoom. A link for that is also in the description. Now go, enjoy the rest of the festival.